So we have coffee and sea posters. Okay? Because Constantino prepared a very long speech. So he is expected to speak a lot. Okay? And we would like to make a photo of the ones that are here at the moment. Some of the participants had already gone, so we better do it at the coffee. See. Yes, it's better to do at afternoon, right before your talk. Before Hans, yes. Yes.
So good morning, everybody. So let's start this session. Today, the first speaker is Professor Ronald Dickman from Universidade Federal de Minas Gerais. He's going to talk about phase transitions in active matter. Professor Dickman.
Yeah, let's use this one. Okay. This has to, where should I click over here? Let's see. Okay, and this is the infamous, let's see, okay, it has a dot. It has, well, okay, we'll see how this works out. I'm no good at these gadgets. So, good morning, everyone. Thanks for coming early to see the talk. And of course, I'd like to say a few words about Constantino Tsallis, who is an expert in many things. For example, he's an expert in Potts models, which I am not. And so maybe you'll catch me in some errors in this talk because it involves a Potts model, but regardless, he's a very generous person, a very interesting person to talk with. And there are a number of chats we've had after dinner or waiting around in a hotel Saguan for some transport to come, where various interesting ideas have emerged, or you've clarified ideas for me. And I have to thank you for the generosity of inviting a mineiro, norte-americano, to join the Institute, the Instituto Nacional de Sistemas Complexos. And I have to thank the organizers, obviously, for making a special effort to get me onto the program. I think it was my fault that I delayed registering, and one day I woke up and said, oh, I think it's time to register, and I was a day or two over the limit. So thanks to everyone for compensating my lack of attention. Okay, so I'm going to try to talk briefly about one of the activities in my group, which involves these three PhD students, Ana Luisa, Leo, and Thiago. And it all has to do with active matter. So I'll try to give a very quick overview of active matter. I suppose many of you have heard about this already, but and then I'll talk quickly about what we're doing. So active matter comprises systems of self-propelled agents, self-propelled interacting agents. They can be organisms, could be cells, robots, brains, The popular examples are things like groups of fish, schools of fish, or flocks of birds, groupings of different kinds of cells that move around. Cellular automata are models. You can build a cellular automaton, talvez, maybe, to model active matter, but where the experimental subject involves animals or robots or things on a shaken surface. For me, cellular automata is a class of models. And of course, we're going to have our models, our favorite models in the active matter area. And in principle, you could use a cellular automaton. So one of the important points about, here we go, about these systems is that each individual has its own propulsion. It has its own source of free energy. And then for life to be interesting, of course, there must be some interaction, typically an interaction that tends to align the velocities in the most well-known examples. So, and another important point, well, this thing is very sensitive. Okay, so another important point is that this leads, these groups self-organize and exhibit collective coherent movements without following a leader. At least that's the belief regarding biological examples, is that there's no leader that is defining the direction. It's something that emerges spontaneously. So with all these ingredients, it sounds almost as if it's tailor-made for people from statistical mechanics to attack. And active matter has some elements that remind us of spin models, because there's a spontaneous symmetry breaking that leads to an order parameter associated with the orientation. But this order is propagating in space because it defines the direction of movement, right? And that is a new element. There's also going to be some randomness, some noise in the communication or perception of the movement, the direction of movement of the elements, of the agents in a given neighborhood. So we can have a classic conflict between order and disorder, randomness, and a tendency to orient in the same direction. So we can expect phase transitions, and indeed the models that are used to describe active matter do exhibit phase transitions. In certain cases, kinds of transitions that wouldn't be allowed in equilibrium. So that's part of the charm of active matter for people from statistical physics. Then there are the people who do the real experiments, and they have to know something about biology more than the physicists do. But there is some give and take between these communities. Okay, so I think that gives the general idea. Here are some quick examples. I think these are called starlings in English. Huge flocks that move around, as I say, without an apparent leader, and form very dense agglomerates. Now, this is interesting because the most popular or original model of active matter, the Vicsek model that I'll describe in a moment, does not include excluded volume interactions. But when things get this dense, you might well imagine that excluded volume is important, as it would be in bacterial cultures where the bacteria are packed together. So that's one of the subjects that I'll be touching on. Other examples, this was a movie, these are bats. Scary to think about, but anyway, bees, locusts, and fish. Very pretty picture. Fish moving around. This is also a movie, but I won't try to show it. And as I said, robots, micro robots. Robots, homogeneous. I don't know where. Somebody's laboratory, who knows? But it's an artificial active matter. Okay, so one of the kinds of ordering that we can have is, let's say, pneumatic, and there are other kinds. I've mentioned briefly the attraction of these systems to physicists, and of course, we want to work with minimal models in the sense that as simple as possible, but still capturing the essential phenomena. We can use theoretical tools, stochastic processes, field theories, simulation, of course, and it allows for, at least in some cases, comparison with quantitative experiments. So let me talk a little bit about the VICSEC model, which was published in 1995, a PRL by VICSEC and collaborators. And it leads to all of these interesting aspects. But as I said, there's no excluded volume in the original VICSEC model. So what do we have? A fixed number of particles. The dynamics in the usual implementation conserves the number of particles. And we have a system with periodic boundaries. It could be three-dimensional or two-dimensional. The original work was in 2 dimensions, and I'll stick to 2 dimensions in this talk. And this is in continuous space. So each particle has a position and a velocity. And these are going to evolve in discrete time steps of a certain duration, delta t. There's a preferred reference frame, the reference frame in which the box, let's say, is stationary. So we don't have Galilean invariance in this model, much less Lorentz invariance, of course. And the only conserved quantity is the number of particles. Good. So all particles move at the same speed, but they have a freedom to choose a direction in the plane or in three-dimensional space. So this is S is a unit vector in the direction of motion, which in 2D is equivalent to choosing a certain angle in the plane. And each particle, as I've mentioned, tends to align its orientation, its angle, S, with particles within a certain radius. The idea is that particles can see or in some sense perceive the direction of motion of other particles, birds, fish, whatever, within a certain region, but not beyond, due to limitations of vision or blocking of the. So there's a local interaction that tends to align particle. And in this assessment of the average orientation within a radius, the particle itself is also included, right? So if we isolate a particle, then what happens? It tends to move along the same direction, except that from time to time, it makes a mistake or there's a noise that causes it to change its orientation. So that's the famous run and tumble model of free swimming bacteria, at least certain free swimming bacteria. And formally, what we have are these 2 updates. Typically, the angle is updated first in each iteration. So we look at the vector sum of the orientations within a neighborhood. This sum is over all the particles in the neighborhood. And we take the arguments. And then we add a noise. Now, the noise can be implemented in various ways. It's not always simply by adding a random number times and amplitude. Here, the random number C is uniform on minus pi, and eta defines the intensity of the noise, right? So that's going to compete, obviously, with the tendency to orient. But you can implement the noise in another way, thinking that each agent, each time it assesses the orientation of a neighbor, it has a small probability to make a mistake. And then these errors will accumulate in defining the new direction of motion. So we update the direction of motion, we update the positions, each particle moves along its current direction, and then this is iterated many times. Okay, so this is illustrated here, but I'll keep going. So we have a few parameters. First of all, we can set delta t and the perception radius to 1 without loss of generality. There's a speed, a noise intensity, and the density of particles. In many studies, this parameter V0, the speed, is fixed at some convenient value. So in the end, we're left with two principal parameters, the density and the noise intensity. And you can already anticipate what's going to happen if you have a high noise intensity. The system is going to randomize and you won't observe any collective motion, and vice versa. If the noise intensity is low, you expect order. But this is modulated by the density, of course. If you have a high density of particles, it will be easier to maintain order.
The ordering of the updating in angle and position, does it make any difference?
It shouldn't really. It's just they're two half steps. So after a long time, what you call a step, whether it's velocity first and position after or vice versa, I don't see why it would make a difference. It's more or less, you could begin with a half step and then after a long time, probably you forget. Okay, so we define an order parameter as if it were a spin model. And here's an interesting point. In 2 dimensions, in equilibrium, if one were to break a continuous symmetry of orientation in the plane, well, the Mermin-Wagner theorem tells us that you shouldn't have long-range order. Now, apparently, the Vicsek model does exhibit long-range order in 2 dimensions, breaking a continuous symmetry. And the point is that the Mermin-Wagner theorem doesn't apply because the system is out of equilibrium, and certain terms that would be excluded in equilibrium in, let's say, a continuous hydrodynamic kind of description are allowed. And so in various works by Toner and Tu, it's been argued that these terms are sufficient to allow long-range order. Now, coming back to the studies of the model, which are principally done in simulations, Vicsek and collaborators concluded that this would be a continuous phase transition. The problem was that they studied rather small systems. 1995, they didn't have such extensive computer resources. And so there's an excitation that occurs when the system is sufficiently large, was the formation of bands. And with these bands, it becomes clear that the transition, in fact, is discontinuous, except in the infinite size limit. So I'm not sure if it's very visible here, but there are some apparent jumps, and more careful studies lead to the conclusion that the transition is, in fact, discontinuous. Okay, so here's a generic schematic phase diagram. You have low noise, higher density. You have a homogeneous ordered phase. Naturally, for high noise intensities, you have a disordered phase, and in between, you have these ordered bands, bands that are moving along, that are almost shock waves, and that coexist with a disordered background of vapor, if you like. Okay, so I'm going to talk rapidly now. How much time do I have left? 17. Oh, that's good. Okay, so here are the projects that we're working on in my group. This first one is a collaboration with Yves Châté, I'm sure many of you know, who's been working quite intensively on active matter. And the idea here is to include particle number fluctuations. So now we're not going to conserve the number of particles. And we're going to introduce a birth and death dynamics, something like the contact process. Then one motivation for introducing this is that in the theories of Toner and Tu, there's a long history to this. It's not a simple matter. And at some point, they discovered some terms that they had forgotten about in an earlier paper. And so in the earlier paper where they claimed that they had exact results for all the critical exponents in 2 dimensions, this turned out not to be so when they re-examined their analysis. But they asserted in the new revised analysis that in the case of a birth and death dynamics, in the extreme limit where the density wouldn't fluctuate, the local density wouldn't fluctuate, that they did have exact results. So this is one motivation. Another motivation is simply that it could well happen in a population that exists for an extended period of time. Let's say bacteria, that bacteria divide and some die or whatever. So it's interesting to include this kind of dynamics. So just to give you a quick idea of what happens, the original Vicsek model would look something like this, a discontinuous phase transition. Here I'm plotting the order parameter versus the noise intensity. And so this parameter nu is more or less the time between population updates relative to the intrinsic dynamics of the Vicsek model. So the original Vicsek model, would be, oh, I really made a mistake. How did I do? Oh, I keep going the wrong way. It's very confusing, because there's an arrow and you think the arrow means go forward, but, and then if you, well, anyhow. So that would be infinite nu. There's no population dynamics. And here I'm contrasting slow population dynamics, which again leads to a discontinuous transition, and rapid dynamics, which almost seems to erase the transition. I mean, the best we can say is that there's some mean field-like behavior, but there don't seem to be critical exponents. Well, I'm not basing discontinuous merely on this apparent vertical line, but on analysis of the Winder cumulant, which shows a very clear signal when a transition is discontinuous. I'll show an example in a second. And hysteresis. So there's a host of signals that suggest it's a discontinuous transition. This graph in itself is certainly not evidence of a discontinuous transition, but there are other. Okay, so turning to the active Potts model. We call it a Potts model because now we're on a lattice. The reason for studying this is to include excluded volume. So we want to have a way of avoiding particles invading each other's space. They have excluded volume. And the simplest way to do that is to impose a lattice structure. So now each site is either occupied or not. Particles are not allowed to jump to occupied sites, and that's much simpler than having to calculate the distance between many different neighbors. So we're on the triangle lattice. Each particle, each site has 6 neighbors, but we only allow 3 velocities in the interest of being minimal, simplifying as much as possible. So these three velocities do allow a particle to visit any site in the lattice. It's a bit like driving around in Belo Horizonte. We have the saying, 3 rights make a left. You can't make a left turn very easily, but if you make 3 rights, it has the same effect. So it's something like that. 3 possible orientations. A previous study by Peruani and collaborators using this idea was performed on the square lattice, but here we have some additional features. We try to do a careful finite size scaling analysis, but some of the states that I'll point out were already described by Peruani and collaborators. So here are the kinds of steady states that we observe on the triangle lattice. At high noise intensities, of course, we're going to see an unstructured mass, well, with some local structure, perhaps, some clustering, but we'll call that the high noise phase, high temperature phase, if you like. That's disordered. Now, at lower noise intensities, the system can order in various manners. And some of these orderings lead to immobile structures. The simplest to understand is probably this that we call an immobile band. Remember that they could appear along the horizontal or any of the other 2 allowed directions. But what happens is that the particles accumulate in 1 or more parallel bands, and the particles inside the bands are stuck. They can't move forward or any place else. But at the frontiers, at the edges of this band, they can evaporate and recondense. So we have a kind of non-equilibrium dynamics of coexistence between a condensed structure and a vapor. Then there are other situations, varying the density, the noise intensity, and the initial conditions. We can have other kinds of condensed structures. So this is a kind of traffic jam in which all 3 velocities are present. It coexists with a vapor. We can have another kind of traffic jam in which just 2 velocities confront one another. And then we can have bands that are less regular. They appear at intermediate noise intensities, and that actually have some movement because the boundary is a rough boundary and allows particles to escape. Of course, inside these bands and inside these traffic jams, not much is going on. The particles are pretty well stuck. Yes, 5 minutes, thanks. Okay, so 5 minutes I think is just enough to close the story. Here's a phase diagram of different kinds of steady states. The blue points are that immobile band. The red points are disordered. And then you see there's a narrow region where we observe some of the other kinds of states. So that's schematized here, vapor plus an immobile band in the noise and density plane. Various other kinds of structures. There can be multiplicity or metastability. Multi-stability is a better word, although there is also metastability. And then the disordered phase. Now, since there's a lot of, there's a lot of parameter space to explore here. What we've done is looked carefully along the full occupation line, density equal to 1, and also along a density of 1/10, right? And we'll get to the other densities some other time. This is hard enough. So what happens on the full occupancy line is that nobody moves. So you have something that looks like a spin model. The dynamics, the transition rates violate detailed balance, so it's out of equilibrium. It looks something like a majority vote model, where you look around a certain neighborhood and you decide to agree with your neighbors with some probability, but there's also a probability for dissenting from the neighbors. And this leads to evidence of a continuous phase transition. You can see here the variance of the order parameter, showing a series of peaks that grow in height with system size. And here we have crossings of the Binder cumulant. And so we have a good estimate for the position of the transition. The critical exponents look like they're going to be three-state Potts model critical exponents, but that's still under study, so I won't affirm that it is. And at the lower density, there are clear signs of a discontinuous phase transition. For example, as I mentioned, the Binder cumulant, instead of going monotonically between two constant values, goes negative in the vicinity of a discontinuous transition, because you have an extremely broad, typically bimodal probability distribution. So here's the order parameter showing bistability. And here, oops, sorry. Here is the hysteresis curve for this low density. Here we seem to be at a spinodal point, whereas here the transition back to order, the loop goes around this way, right? When we come back, and there seems to be a nucleation mechanism involved, because the position of the transition back to order is quite variable and involves nucleating, let's say, a band of a critical size. Okay, so I guess now we have mean field theory, both uniform and also spatially structured, that allows us to study the stability of these bands or traffic jams. That's work in progress, but it's going nicely. And okay, so here's a summary. And okay, I think I don't need to read that to you. Okay. And so I want to say happy birthday. And I thought I would show one image because it relates to what Professor Guillemard was talking about yesterday. See this urge to explore what we can only see, what's partially hidden. But I think this image from my neighborhood in Belo Horizonte illustrates this in a funny way. So, did I go over?
We have time for some questions. Gymnastics.
Thanks, Ron, for this very nice piece of work. I was wondering whether in the VCheck model, whether there is always a single connected cluster, or you have fragmentation, and if once you put population dynamics, that may change, you fragment more or less.
You're referring to the original VCcheck model.
And when you put population dynamics, whether it changes or not.
Well, I would say it depends on the density. You could have a uniformly ordered phase in the Vic-Sec model, but at low densities, you might just have a swarm that wanders around and it's more or less compact. That can happen as well. In the lattice model, we also see both. We can see something quite uniform at high densities, or just these structures that I've mentioned. Now, the band, the immobile band, of course, has to wrap around the system in the periodic direction. Otherwise, it wouldn't be immobile. The other structures that are a bit more complex and sort of irregular don't necessarily wrap around. For example, this traffic jam could just sit in the middle and be a compact structure. And you could have multiple traffic jams or multiple bands. I mean, all of these things can multiply depending on initial conditions.
Final question.
Can you go to the next slide?
This one?
Yeah, that one. Can you imagine, is it possible to imagine a mechanism in which the phase transition would come back?
A re-entrant?
Yes.
Which way?
No, that way. This is to say the disordered phase to be larger.
Yeah, can I? It's conceivable. I mean, you probably have to add a new element, like
Yes, that's my question.
yeah, if high density confuses the agents, that seems plausible. I don't know if anyone's ever looked at that. It could be.
Time for a very short question. No. You do a short question too. No, but then he will.
You're wasting more time.
What happens if you have 3 states, but more states, Potts model? More directions.
Yeah, the best answer is I don't know, but I'll hazard a guess that, of course, it'll have the symmetry of a Q-state Potts model. And so we might see discontinuous transitions, even at full occupancy. And yeah, that might be a better model for bacteria. In fact, maybe you could build a substrate that sort of forces them to go along these directions. Yeah.
Okay, let's say we have two active matter different systems, because when you say states, they are the same kind of active matter system. But when you have is there any simulations where you can have two different kinds of active matter systems interacting?
I'm not aware of that. That's interesting for several reasons. There's a phenomenon called mobility-induced phase separation, where within a given population, you have particles, some particles that are more motile than others, and this can lead to an interesting separation. But two, let's say, autonomous active matter systems that somehow interact, I'm not aware of. There may well be. I mean, there's a lot of work in this area, and I'm not an expert on all the. There's a huge area also of wet active matter, where hydrodynamic interactions are important, and I didn't touch on that at all.
So I cannot say no to Suani. She's asking.
It's a very simple question. Dickman, how extensive is the concept of active matter? It's a very fundamental question, because in some sense, it's used in a very general, but otherwise sometimes it's not so general. For me, it's confused all the time. Also, you talked about.
But your question is how extensive is it? Yeah. Yeah. Sriram Ramaswamy has a review article in which he really tries to give the criteria. But I would say you have to have some sort of self-propulsion. The energy is injected at a small scale, not from outside. And then there are some interactions between these elements. So, for example, a driven lattice gas, which looks, or traffic models. Well, traffic models, yes, because each vehicle is, let's say, autonomous and can make decisions and is self-propelled. But a driven lattice gas, in the usual sense, is not active matter because the direction and the drive come from outside. There's nothing, each particle just follows some stochastic rules with a bias. So that wouldn't be considered active matter.
So let's thank the speaker again, please. Next speaker is Professor Haroldo Campos from INPE, Instituto Nacional de Pesquisas Espaciais.
No, I can't see what I'm doing.
Isso, tá legal. Ótimo. Peraí. Hello. Esse. É, esse. Pointer is here. This is the one. Wow. Wow. I'm sorry for that.
Cadê o rapaz? Tá lá em cima, né?
É digital. Ele aparece ali, ó, tá vendo? Ah, tá. Esse aqui é físico. Tá. Não, então tá. Digital a gente ponta para ali perto. Se quiser esse, tem esse também. Esse é o comum, esse é o digital. Digital perto aqui. Okay. Good morning. Good morning, people. Thank you for our chairman here. My name is Haroldo Fraga de Campos Velho. I am a researcher from INPE. This is acronym for National Institute for Space Research here in Brazil. And I want to say thank you in particular for this motivation to be here. I'm very happy to be involved in this celebration of this birthday of Constantino Tsallis. Okay, and so my idea here is try to do some outlines about the non-additive particle filter. I used to say non-extensive particle filter, and so Constantino, in a previous conversation that we did some weeks ago, months ago, I mean, and so I changed a little bit this this expression. Okay, so I'm going to do some when this is this interaction with the Tsallis idea in this non-extensive thermodynamics starts. This is probably my colleague in INPE, Reinaldo Rosa. The next speaker here is going to do more details about this kind of interaction and probably more more examples of application of these ideas with us. And then I'm going to do this is a kind of robot. This is aerial drone for autonomous navigation. How can you do that? But without using GPS sign. And I'm going to explain why we need to do this, in particular when you applied some of these devices over Brazil. Okay. And well, there is some ideas here in order to this autonomous navigation using visual odometry, computer vision. And then you can do, if you have more than one information about the position of the drone, and then you can combine all of this information using a data fusion by using non-extensive. I'm recover the previous expression, non-extensive particle filter. Okay, let's go. And so I'm start to do some applications that our group in INPE has using the Tsallis idea, and I start with atmospheric turbulence. And then I'm going to do some words about how can you apply this in order to describe some structures in the universe. And then some applications for inverse problems, and finally, particle filter, new approach. Okay. This is, by the way, mentioned about the atmospheric turbulence. And so let me to introduce, this is a kind of Tsallis storm when he is one of our speakers in the School of Emergent Science. This is one school, the coordinated over there, Reinaldo Rosa, and Reinaldo invited Constantino Tsallis to be there. And this a kind of start point for this Tsallis storm. Okay. So just in case, if you're talking about atmospheric turbulence, so maybe this is a good expression mention about storm. Okay. All right. And then let me to do some few words about how people try to understand turbulence. In general, the people understand turbulence as a kind of vortex with different scales. And so on the left side here, this is the former idea. I mean, we have vortex with different diameter, for example, and so the diameter of this vortex would be smaller and smaller and smaller. However, all of this vortex in different scales is going to complete all the space. And then if you travel, imagine that we are a very small traveler, and then you are crossing all of this area here. And so doesn't matter what kind of scale you are going to feel the sensitive about vorticity all the time. All point, independent of kind of scale you are. Okay, but however, the people imagine that when you are going to do some experiments, the scenario is something like that, and then you don't have the filling out all the space with vortex. And so if you are, again, a traveler in this direction, and so you have zones with intense vorticity, and there are zones there is no vorticity. This is intermittence. And how can you describe this? Using statistical behavior. Okay, one idea is to use non-extensive statistics in three-dimensional fully developed problems. This is a paper published many years ago, more than 2 decades. And this is one idea from Fernando Ramos after some talk that Constantino did in that school. And so the idea is, how can I represent the statistics that depending on the scale, and for different scales, I have different probability density functions. And then we have this Q-parameter. When you change the Q-parameter, you change the probability density function. And so this is one idea that you try to test it. And surprise, when you compare the data from the experiments, there is a good matching with theoretical PDF. And in this particular case, I mean, turbulence, also you can derive analytically the Q-parameter for different scales, like this. And so you can compute this appropriate or more adequate, more matching of the Q-parameter. And also you can see that numerical calculation of Q-parameter have a good matching with theoretical one, analytical one. What? R is the scale. R is the scale. And so here, yeah. And so this is, let me see here. I need to go back. Oh, go back. R. And so actually you are going to compute the gradient of velocity, and this gradient depending on the scale. And so R is the scale. Thank you. Thank you. That's a good question. Help me. All right. Well, but what are interested to do this better understanding about turbulence? Because turbulence, it's a permanent feature of atmospheric dynamics. And in the middle of the last century, we start to use numerical weather prediction. That is a scientific conquer in our times. And this is one important issue when you have computers. Okay, and then, well, but you need to solve this kind of Navier-Stokes equation. Believe me, this is a kind of Navier-Stokes equation, and this is solved all the time for operational centers in order to predict our weather, the atmospheric dynamics. Okay, and the turbulence is a permanent feature in this kind of application. Okay, how can you represent it? Well, one idea to represent the turbulent flux or Reynolds flux is try to do some kind of gradient of the mean quantity, for example, speed, velocity, wind components, and multiply by one a diffusivity. In this case, turbulent diffusivity. And so all of physics about turbulence is concentrated in this parameter. But it's a little bit complicated here in terms of atmosphere, because during the day, we have one thermodynamic regime, and then this thermodynamic regime change at night. And so you have different thermodynamic regimes, and so to need to take into account all of these conditions in order to represent the turbulence to be taken account in Navier-Stokes equations for numerical weather prediction. And there we go. This is our approach using to represent the eddy diffusivity, okay, or turbulent diffusivity. This is sigma here representing the variance of wind. Beta is a parameter. This is when you have two, well, you can represent, for example, fluid dynamics using Eulerian or Lagrangian point of view. And this is when you're going to do the spectra using different approaches, Lagrangian, Eulerian. And so this is a kind of shift. The spectra is the same, but there's a kind of shift between, and so this shift is beta, okay? This parameter represents this shift. And so, but we derive previously the Lagrangian approach, and then we try to recover to the Eulerian description. But in order to do that, you need this parameter beta. Okay. I'm sorry if I'm doing some details or if I got not a lot of details that we want, but the idea is to do a kind of a big picture scenario about that. All right, but one thing that's very interesting is this guy here. This is the spectra, the turbulent spectra. I mean, the spectra representing the turbulent kinetic energy. Okay, so there we go. This is our energy. This is the zone where the energy, the production of energy, when the entrance of the energy here, and so the inertial subrange here, and then this the end of the spectra. And the idea is to do some kind of analytical expression for this. In order to do this analytical expression, I need to introduce some good physics. I mean, for example, the maximum of this spectra should obey what we have observed in the nature. Secondly, we have, as you know, in this domain here, there is -5/3 law Kolmogorov, I mean. All right. And then try to do some kind of arrangements. But when this exponent here, zeta2, it's equal 2/3, and then you recover the standard Kolmogorov law of turbulence. However, if this exponent it's different from this idea, and by the way, if you are going to take in account the intermittence, this exponent should be different from 2/3. But, you know, this is a kind of equation. There's this dimension balance. And so if you put other number in this exponent, you are going to break this kind of, and so you need to do something else. And so this is my generalized Kolmogorov equation. And that is idea in order to do some good matching between Tsallis statistics applied to turbulence and using a parameterization for turbulence. And this is multifractal model for eddy diffusivity and counter gradient term in atmospheric turbulence. But this is during the day. Okay, so there is some difference between standard Kolmogorov, this is curve, and our between quotes here, the correction. Okay, using a non-extensive. And so this is, I think, take care about my my words now. I think that is the first parameterization for turbulence that put in account the intermittence in the parameterization. Okay, but this is during the day, and then at night, representing intermittence in turbulent fluxes, an application to a stable. The people in meteorology don't say nocturnal. Sometimes they use, but more frequently they say that in this condition, the stable atmospheric boundary layer. And there is some difference again. Okay, but again, the size of storms continues. Okay, and so description of the structures in the universe. Multi-scale again, non-extensive for large-scale structures in the universe. Maybe Reinaldo is going to do some more details about that, but few words, the idea is, again, the space scale, it's in the horizontal axis, and the correlation dimension is in the vertical. And you can see that larger structures is going to convert the homogeneity in large scale for the universe structure. It's interesting, and this, in order to do that, you need this kind of statistics. Long range action, and one idea to do this taking account is Tsallis statistics. Okay. Extreme events dynamics, information of galaxy size dark matter structures. this is one, because when this extreme event, it's not frequent. And so the statistics about this should be different from the regular or more frequent events. And so you need to do other statistics, Gaussian statistics or other simplified, between quotes, this simplified, that is more frequent that you can find in the literature, doesn't match. And so Pareto, this is good contribution. But one important in this paper is in the conclusions. I extracted this part of the conclusion. In summary, they said, we have obtained complementary results that reveal turbulent-like structures. Remember, turbulent structures in the universe dynamics. And I show you that you have some ideas. How can you represent or parameterize the turbulence if you are interested to use Navier-Stokes equation approach for that? Okay, so if you reveal some turbulent-like structures that would be normally remain right in the instantaneous density plot simulated from lambda CDM model. In addition to characterize, we have shown in this paper, further investigation can apply to GEV. This is a generalized extreme value statistics to distinguish different versions of cold matter model, including possible more realistic lambda CDM extensions, for example, to align quintessence rather than a cosmological constant. This is to be investigated. Okay, again. And so one my colleague here is retired now, Sandra Sandri. She's an expert in artificial intelligence, if you like, computational intelligence. Camilo Rodrigues is an associated researcher in the cooperation with Reinaldo in this project of emergent science. And the first author, well, he is in the audience here. Okay. But this is just one comment and applications of inverse problem. Well, as you know, inverse problem, you can obtain regularized solutions for that. One of regularization methods is Tikhonov regularization. Another one, it's employing entropy. Okay, entropy. Why not non-extensive entropy? Well, but you can do more than that. You can unify the regularization theory using the maximum non-extensive entropy principle. And this is the theorem. For particular values for non-extensive entropy, for example, non-extensive parameter Q, it's equal 1, and so you recover, all people here know that, you recover the standard Boltzmann-Shannon entropy. However, if the parameter Q is equal to 2, this is equivalent to Tikhonov regularization. And then if the parameter Q for inverse problem, and inverse problem, we're not talking about Shannon entropy or thermodynamics entropy, it's a shape entropy, because we try to identify the shape that we don't know. But you know that from the data, we try to extract some shape of this that we are interested in. And then this is a shape entropy in terms of inverse problem. Okay, but in this paper here, they only use Q equal 1 over 2. It's Rebolo, Neira, Fernando Rubio, and Plastino, Professor Plastino. But actually, you can use different values for that. And in particular, for example, here you can see here using different values for this Q parameter in order to recover the retrieval here of the vertical profile of the temperature, but not only temperature, but also you can apply this to recover humidity, gas concentration, whatever. But this is from satellite because satellite is going to measure what? Radiance. And so you try to extract some other information, temperature, humidity, whatever. Okay. Wow. Okay, and so again, you can use some other methodology. For example, artificial neural network. One neural network is radial-based function. Radial-based function, in general, the people use Gaussian function. Why not Tsallis statistics? And then I created the non-extensive radial-based function. And the best results using, this is my neural network, by the way. I used to say, okay. Okay, then the last time of my talk, I'm going to do some introduction, some words about aerial drone autonomous navigation. And we're going to use images instead of GPS signal or GNSS signal, or Global Navigation Satellite System. Why? Because, I'm sorry here, whoops. I'm sorry here, malicious attack. If you are doing this kind of signal, one could be attack you of your system and take your control of your device, your drone. And so how can you avoid this? Well, you don't use GPS sign, for example. Secondly, and more important, natural phenomena. For example, scintillation. Scintillation. Okay, what means scintillation? Scintillation is because ionosphere, it's not a homogeneous layer. There is some fluctuations in these concentrations of ions in this layer, and this kind of different concentration is going to interrupt or can be change this signal of the satellites, in particular GPS signal. Other things is ionospheric bubbles. As you can see here, these ionospheric bubbles, it's in the tropical and equatorial zones. And then this discovered by my colleagues in INPE. Well, how can they do that? Well, in the rockets, they have sensors, the sensors capture some data from that. And so we try to interpret this data, and then the people realize from my colleagues there, oh, this is not described in the literature. What's that? What's that is ionospheric bubbles. And so this medium or high latitudes, countries like US, Canada, England, Denmark, Germany, whatever, Japan, I don't know, maybe also our colleagues in Argentina, Chile. This is medium and high latitude countries, and so you can't identify this. So you need to be in this latitude in order to capture, to take data. And so this appears, and we realize, and by the way, Brazil is in this one. And so if you want to do GPS signal, in order to do some deposition of your drone, take care. Maybe this doesn't work, in particular for this ionospheric bubbles. Okay. This is another thing is this is production of ions. This is equatorial spring effect. Equator, it's there is more light that you have receiving on Earth. Okay, and then this is the zone of the planet that you have more production of ions in the atmosphere, the ionization zone here actually. Okay, and so this, but if you in the middle of night you wake up and what happened in the ionosphere now? Okay, you can sleep again. Well, because we did some kind of, like meteorologists, we did also operational prediction of the atmospheric dynamics. And so in the on the upper side of this figure here, you have 3 different times for representing the concentration, electron concentration, and this day in 19 March 2011, and this is other during the summer. We have much more intense activity of sun, and then that is the idea is how can you, for example, you can capture different images. If from these images there is some kind of overlap, and this overlap, and so you can also identify where the drone is, and so this is visual. I mean, visual odometry, and the idea is the blue here is the trajectory made by drone, and here you can do something different, like, for example, extract some edges from the image, and then we have to do some treatment in this image, and after that you do some kind of correlation between one georeferenced image and the image obtained by the drone, okay? And the maximum correlation is the coordinate of drone. And this matching is a computer vision positioning of the drone. I don't know, let me jump this. Okay, and this, the computer vision have a better results than the odometry. Okay, and so we have two estimations of the drone position. One is from the odometry, another from computer vision. And I to do this kind of data fusion using non-extensive particle filter. This is pretty standard. I mean, when I'm going to do use the Bayesian strategy, particle filter, okay? But this is one thing that they are doing in order to compare two different PDF. They are using this operator here, and then this is a problem, because if you are dealing with a stochastic dynamic process, and this stochastic dynamic process is Cauchy, but we are using this likelihood function here, Gaussian one, and your prior PDF is Gaussian, how can you arrive in a Cauchy distribution? You can't, actually. But again, if your prior is Cauchy, and then your likelihood function is a Cauchy, how can you arrive in a Gaussian? Imagine that. And so how can you do that? That is, where is the attractors in terms of the distribution of the, I'm sorry, Mr. Chair, I'm more 2 minutes. And so the Gaussian and Levy distribution, this is central limit theorem, and Levy-Gdenenko central limit theorem for. And then you have two, and you can apply the Tsallis distribution depending on the Q value that you are going to use this. And so the idea is to matching in order to identify the best Q value for this likelihood function. And after that, there is some theoretical stuff here. Again, when you are using this approach, also you can identify the confidence interval. Okay, not only to estimate the position of the drone, but also this envelope of the confidence interval here. And then my final slide. This is the error when you are using different methods for drone positioning. It's odometry, computer vision, standard particle filter, Q is equal 1. And then if you're using a more appropriated value for this parameter here, you can see that the error that you are flying, it's going to be down. Okay, there's some technological stuff. The idea is to revisit, for example, this is one. Svani, it's our guide here, and estimation of tumor size evolution using particle filters. The idea is to using this non-extensive particle filters, and for data assimilation, this is a very important process, and blah, blah, blah. If you're interested in this data assimilation using Kalman filter, particle filter, and beyond means non-extensive particle filter, adaptive particle filter. This is on the internet, in YouTube, and happy birthday, Dr. Constantino Tsallis. And thank you all for your attention.
We have time for one question.
Can you explain what is a bubble in the ionosphere?
A bubble. Okay. Well, when there is some, as you know, there is no kind of homogeneous density in terms of electrons in the ionosphere. And so when you have this kind of zones with very low density, you can call this as a bubble. However, this bubble, it's not in, no, it's not be stationary. There is some dynamics. And so this is, for this, we need to take into account all of these dynamics in order to identify when and where your GPS sign is going to work. Okay.
Okay, thank you very much for
Thank you.
again. So this time is Professor Reinaldo Rosa from INPE as well.
Yes, okay. Okay, okay. So, good morning, everybody. So that's big pleasure to be here and to celebrate the Constantino's birthday and see old colleagues and making new friends also, of course. And let's see, I would like just to show my collaborators in this new approach that we started just a few months ago. So that's Ruben Salter, ex-PhD student in our course, Applied Computing. So now he's a postdoc. And Luan Baraúna, he's from Universidade Federal da Bahia. And Érico Hempel, it was also my PhD student. Now he's a professor in ITA, in São José dos Campos. And we have also the collaboration of Juan Valdivia from Chile and Alejandro Freire from University of Wellington in Victoria, New Zealand. So, of course, that's a very special meeting. So I cannot avoid to start my presentation with a timeline that begins in 1998. Okay. So I do that especially to bring you on that topic, why we are doing that now. So that's the history. So to understand why we get, oh, sorry, Constantino, just, okay. That's very good. Okay, so let's start here. It was the school that Haroldo was talking about that. So it's the first Brazilian school in emergent science. It was supported by FAPESP. Okay, it's a long time ago. So let's test Constantino's memory. So do you remember this lady? She stayed at talk about you 2 months after the school, every day. Oh, Constantino is very, very funny, very good guy. So Christina, do you remember? Christina, she was taking care of you many times when you went to INPE. So that's the reception of and it was me and also Camilo Rodrigues Neto was collaborating with us in that project. I think so, yes. Camilo was here for a couple of days, yes. So we did this meeting. So Constantino was there. I think this guy is very famous, Gandhi, right? Our friend. For Natal, yes, sure. And that was the team that was there. So we have Celso Grebogi, Constantino here, Camilo, Jorge Albuquerque Vieira. I'm not sure if it's still alive. Maybe I think he died a year ago. Nestor Katisha, Zorzenon, and many people here. So there is one special guy here. Where is Wally? Who is this guy? Can you recognize this guy? He's very famous in this meeting, right? Okay, I improved the photo. Maybe now it's better to see him here. If you don't recognize, Well, now it's impossible. So Ernesto is here. So he's here. Okay. It was a nice dinner in São José dos Campos, 1998. You remember that? Yeah. I think so. So this is also a very important moment in our team when we were to Cancun, Mexico for StatFest 21. And at that time, two students of us, Maurício Bolzan and Adriana Materi, start to the activity in our graduate program. So in that time, I don't know if Constantino remember that. Tsallis introduced me Rosário Mantenha, and Rosário Mantenha was the co-advisor of Adriana. She stayed for 2 years in Italy, 1 year in Italy, and it comes this thesis and then the papers. Okay, it was published in 2004, 3 years after this meeting, when Adriana finished her PhD. There is also this moment, very special one, when I brought Harry Sweeney from University of Austin, University of Texas in Austin. Sweeney was here with this support also from FAPESP. So I asked to Constantino, do you want to meet this guy? I said, oh, that's the guy of the Jupiter spot, right? The guy that will explain how the Jupiter spot behaves. So, and so Harry came to CBPF. We stayed here for, I don't remember, maybe 2 or 3 days. We discussed in our room. And after that, what happens? They organize a meeting in Los Alamos about this topic. This is a preface wrote by Sweeney and Constantinos. In that same issue, we published this paper, but a surprise for us, we got a honorable mention. Fernando Ramos was there, so it was for our team, me, Haroldo, and Fernando, for those papers that we published before, okay, for the pioneer work applying statistics in turbulence. So it was a very interesting moment in this timeline. Okay, so we publish some important results in solar physics and space physics. Okay, so that's one special paper, very old one, 2003, about non-linear distribution of sunspot magnetic field, but using 1D data, only the data that Ernesto was showing to us in his talk. So that's the solar cycle. Solar cycle is related with the dynamo. Dynamo in that time was only simulated using 2D dimensions. And can you, this movie, please? The guy is there? No. Ah, okay. Now it comes. Você roda para mim, So that's the 3 dimension that comes from the MGD equations. So the dynamo is the simple dynamo. It's quite easy to understand. You have the poloidal field, and then the poloidal field by differential rotation in the plasma is frozen in the plasma. It becomes a toroidal one. So when the toroidal one by radial instability comes out of the sun, we have the sunspots, and that this number is in this very interesting cycle of 11 years. So what we did also was applying the generalized thermal statistics to find out some non-Gaussian time scale fluctuations, typical ones. So we found some Gaussians. I don't remember, maybe Q here is in a range from 1.4 to 1.6. And we found this 16.9 hours during the variation for the whole year. We applied the wavelet analysis here. We got this high frequency signal, and we got this application. But all of those applications for one dimension. So now we move it. It's time to move it to the three-dimensional, and also, of course, we can get slices of those simulations. We have now very powerful simulators. This is the Camellia that simulates in 3D the evolution of the solar wind from the sun to the interplanetary median. And we have also Pluto and Pencil. That's a collaboration. This is from Paul Charbonneau from Canada, and it's Canada and France. And Camellia is from a European consortium, which is leading by Italy. Okay, so we have those very beautiful patterns, and we are in a new frame now to understand, to classify those patterns, to following the patterns, the pattern formation in these spatial temporal complex systems. I call complex because we have at least two properties. One property is the nonlinearity, all those underlying physics that are generating those beautiful patterns are nonlinear, okay? And also we have the noise component, okay, because there's a real life, the simulation for real life. And also in cosmology or observational cosmology, I'm not going to talk about that because I will exactly the same, not the same figure, but the first figure in the paper, but this is two correlation function. We start from these ansatz for the scaling related to Q and this free parameter beta. So then we can have the correlation dimension, the 2-point correlation function is a function of correlation dimension, and correlation dimension is a function of Q. Okay, so then we can get, comparing to the real data for around 10 megaparsecs of size in the sky, we got that all the fluctuations we see are non-Gaussian. It's kind of we can use a multifractal or maybe another approach, but it's for sure it's not homogeneous. We can see that. Okay, it's come. Yeah, okay. So that's a 3D simulation for the large scale structure formation in the universe using dark matter, and that's the lambda CDM model. So it starts off a redshift like 40 and goes to 0. That's the present time. But what's interesting here, we can do that. This multi-scale analysis, you can see simulations in a very, very small scale. Can you? So what you see here, you see the gravitational collapsing interaction. You see now that's a very interesting to see this. Okay, it goes there. It's here. Okay. So when you do the fitting for the log of the density as a function of internal scaling like this, okay, we can have 6. We got 2 different scales here, okay, between 130 megaparsecs and between 30 and 3 megaparsecs. What you see the same law. What means that in terms of fundamental physics? That's very important question. What do you think about if you see what we expect a kind of gravitational collapse? So there is no gravitational collapse in just one way. When you see the particles, they go and they go far from each other, and then they come and they do like this. Okay, so that's totally a non-Gaussian process. It's not a diffusion or anti-diffusion, like it goes like this or it goes like that. It's go like this. Okay, even you can see this in very fine details here. So that's a very, very interesting characterization of the whole of gravitational instability in cosmology. Okay, so now you understand why we went to the 2D dimensions, 2D plus 1 dimension. So I'm going to show you the ongoing research that my group has done. So that's one very interesting cube. That's a cube from Zeus simulation. That's entropy pattern from turbulence. Okay, so that's very, very rich simulation for information on the scaling that we see when we want to understand voids and filaments, non-Gaussianity in 2 or 3D dimension in spatial temporal domain. So Constantino, I don't know if you remember, but I have this gradient pattern analysis. That's the technique that I created my PhD. We have using that for many years. So one of those papers, I think in the acknowledgements, Constantino is here. He was at INPE. You gave him the idea to use a log scale because the number was asymptotic way to the dimension of the image. So we did some applications of this idea, but nowadays this is a very recent paper comparing to this one. We applied that for galaxy morphology. Okay, gradient pattern is very simple to understand. If you have an image like that, you have a central source, a heat central source. If you take the gradient of this matrix, okay, this is totally symmetric. You can also have a Besselian, for example, in 2D. So it is going to be bilaterally symmetric, horizontal, vertical, and diagonal axis. So if we start to remove all the symmetric pairs, there will be no alive pairs of vectors here. Okay, so when you break symmetry, a little bit bilateral symmetry, any place of the image, and we start to remove, there will be some alive pair of vectors. So we use this asymmetric vectors in a, we can calculate the first gradient moment, it goes by 2. So this is the Delaunay triangulation among all the asymmetric vectors. Okay, and this is G2, this is related to the norm of the vectors in the gradient field, and we can also calculate G3 related to the phases, and also a G4 if we have a phase and norm in the same equation, like entropy, for example. And we did that for 100,000 of galaxies, and we separated quite well, okay, the spiral from the elliptical ones. Elliptical ones are very old galaxies, so the astronomers, they like to work on elliptical galaxies, and so that's one of those applications. But what's the problem here? GPA is not a good tool because GPA has a very high computational cost. Because you see, you start doing the gradient field, so we compare each vector, you are removing symmetrical pairs. It means they have the same norm and opposite phase for a given tolerance, of course. So we remove the pairs. But computational goes to n square order. So it's not a good one. So we have applied for some applications, for example, Ginzburg-Landau equation. So GPA can catch a kind of oscillatory relaxation for the spirals. Okay, and for also couple maplets in 2D using 3 gradient moments of triangulation, norm, and phase, we can get also those transitions to relaxation regime, a noise relaxation regime, of course, and it works for some applications. But now the analytical challenge that we are facing on is related to this. We have a mathematical computational operator here. It acts on different kinds of spatial temporal pattern formation systems, different systems. So I would like to have the 2 best parameters in this parameter space where I can classify different systems that give him different spatial temporal patterns, complex patterns, where the underlying process is nonlinear, we have noise, and so on. And they are big. So usually they are big to see interesting features. So we have terabyte data here. That's one problem if you want to do that in very huge simulations, or even for very huge data that are coming from the big telescopes for the next decade. So we are facing on right now, LSST is coming. Also, we have SKA in radio astronomy. So you have many, many challenges for spatial temporal classification of those sources. So we need things like order n log n, okay? So that's the best para mathematical computational operators that you are trying to find out. So in 2019, those guys published this multi-scale Tsallis permutation entropy. Okay, I don't know if you know this work. It's interesting because it's based on the idea of Bandit and Pomp from 1991. Okay, they do the same thing, but they use your entropy. So they built this OrdPy package. It's a red, straightforward to use. If you want to apply that, it's very easy to use. It's a very interesting package. So what we did, we have input many different systems here. We do a pre-processing image to get the image in the grayscale, and with this size is 64 by 64. So then we transform that in one-dimensional vector, okay, and we apply OrdPy. Ruben Salter is the student responsible to some adaptations on that, because we brought also what we call not only permutation, Tsallis permutation, but spectral entropy, Tsallis spectral entropy. So what we do here, you have this in this pipeline. We can, of course, we can do we can take probability from the histogram, the pure file, but you can also take the spectra, okay, the power spectrum density here, and we can have a probability from the spectrum density value. And of course, using the bunted Pomp, we take some patterns for when you're choosing a window, amount of points. If I can do that with 3 points, or I can do that with 9 points. If you do with more than that, so we go to a low computational performance. If we do that in this limit, we know that d factorial is the number of different patterns we have here. So we go with that in those equations. So if we calculated the probability using the channel entropy, we have the banded Pomp approach. That's the blue one here. If you go to Tsallis permutation, of course, when Q is equals to 1, we go to this limit, everybody knows. So we have the Tsallis permutation. Doing that on the spectra, we have a channel spectral, and that's Tsallis spectral analysis, okay? So we have a 1, 2, 3, 4, 5, 6, and GPA can also, we can use the G4 from GPA. So we have the output, okay, many parameter space, okay? So now we need to choose which one, or maybe 2 or 3 are better to classify different kinds of input spatial temporal patterns here. So we did that with simulations from complex Ginzburg-Landau, Pension, Pluto, and Camellia. So we got here a plethora of classifications, you see. So we use here G4. So you know very well this kind of analysis. For some data, we don't have too much data, so we don't have a distribution right here. But just to show some preliminary results, that's a spectral Tsallis, I guess, the spectral channel. So we we have this sector for Ginzburg-Landau patterns. We have this sector for noise patterns, pure noise patterns. This is a Brownian one. And that's the sector, special sector that we made this zoom here. We zoom in that here just to see that here are the patterns from simulations for solar wind, solar dynamo, okay, and that's the pure turbulence, the Navier-Stokes turbulence. So we have this classification. Here we got permutation Tsallis and spectral Tsallis. Okay, so we gave another. It's very interesting to see that the sector for the Ginzburg-Landau patterns are almost the same sector, but changes for this one. We are still trying to understand which one is better and what's the relationship among them. And but it seems that it's a very interesting approach. Future work. Okay, we needed to do massive application criteria, define a criteria, okay, to generate massive data and to filter up this, trying to filter up and find new sectors on that parameter space. Explicitly marking dynamics, it means that we are not doing a temporal distinction where are the values, but we can use different colors, for example, and we see where those patterns is going during the evolution in the same parameter space. And that's the most important thing. We can use both best parameters as labels for deep learning, for learning functions as an input for deep learning models. So we can have automatic classification when you have terabytes of data and to do this kind of analysis. That's the new fashion everybody knows. So thank you. That's my gift to you, okay? That's actually is your gift to me. I have a learning on non-additive Tsallis fundamental physics. I change here, okay? Non-additive Tsallis fundamental physics about tear and shear process. I think that's very important. When I don't know if Hans Hermann remember that when we were coming back from one of those international meetings in the airport, we are discussing about this, and he was the first guy that told me there is no extensivity. It's wrong. It's no additivity. So we start to discuss this. If you have an entropy for the paper before the tearing, we have one entropy. After the tearing, you have the entropy for that piece and that piece, and we have new information. The entropy of this sector, new sector, even you use a laser to do that, you have some new information. So you have no additive entropy, and we can do very good physics with Tsallis approach. But also important for shearing, you know, if you have not just shearing, but when you have two different density systems doing shearing, okay, that's a very important application also. And I still didn't see one fundamental paper about that. I'm waiting for. Okay, so I invite you, or I don't have time actually, but you know, let's try. Okay, thank you very much. And that's almost December, so Merry Christmas for everybody. Thank you.
So I have time for some questions.
Yes, thank you for your talk.
Thank you, Robert.
Right. You chose several ways of computing PI, the probabilities. And when you take any limit, for instance, thermodynamic limit, do they converge? How do they?
Yeah, that's a very important point because you know, in the banded pump application, they discuss this limit related to the
the kind of PDF you have for the, that's why we use actually, we also came to this, you know, you take all the vector, you take the histogram, and you can calculate the frequency as a probability, and you take this value and you go to the formula. Okay, but in terms of just find out a value for a characterization of the pattern of this kind, that there is no this kind of discussion. But when I go to the underlying physics that is generating the pattern, I think that's a very important question. And they don't discuss that too much, you know. They say if it's the non-Gaussian, we needed to put that in we need to find out some limits to these thermodynamic limits for the pattern formation. Mainly because we are also dealing with noise. In the real data, we have noise, right? So red noise, brown, white noise mainly, and pink noise, all those kinds of 1/f noise. Especially in 2D, also in 2D, right?
More questions? So if not, let's talk. Thank the speaker.
Thank you very much.
Organize this 20 minutes for the coffee.
Yes.
Let's start the session. So now we're going to have Dr. Annalisa Greco, Professor Annalisa Greco from University of Catania. She's going to talk about the application of key statistics to acoustic emissions of compressed construction materials approaching failure. Please.
Thank you very much. Can you hear me? First of all, let me thank the organizers for giving me the opportunity to be here. It's a very great pleasure and a very great honor to celebrate Constantino's birthday together. Maybe I am one of the most recent Constantino's acquaintances because I heard so big numbers. I have only known him for 5 years, but even if it's only 5 years, I consider Constantino a good friend of mine. I'm sure it's the same thing for him. I met Constantino 5 years ago during one of his several visits to Catania. Yeah, of course. We were having lunch in a small restaurant close to the university that Constantino knows very well, together with Alessandro Pluchino and Andrea Rapisarda. And I'm sure that Constantino was having his much loved prickly pears that he loves very much. I was introduced to him, and as soon as he knew that I was a civil engineer and therefore involved in collapse of structures and behavior of construction materials, he proposed, he had one of those millions of brilliant ideas and intuitions he always had. And so knowing the existence of acoustic emissions produced by compressed materials during crack propagation, he proposed, why don't we use statistics in order to give information on the breakdown point? So that's how it all started. Just to give some information, acoustic emissions are elastic waves caused by crack formation, and they propagate in the medium, in the solids, and can be recorded with some sensors applied on the surface. This is a test which is very crucial and very important in civil engineering and structural engineering, because it can allow to detect eventual formation of hidden defects or cracks at the beginning, just monitoring continuously the structure and comparing the response or the static or the dynamic response of the structure with the one of the undamaged structure. So you can realize something has changed, something has happened, and you can prevent failure, of course. So what I will present are the results of two kinds of experiments. The first one was some tests performed on cubic specimens of concrete and basalt in our department in Catania. We did it by ourselves with Alessandro and Andrea. And the other one are being done by Sergio Vinciguerra, who is a geophysic in United Kingdom, the laboratory of University of Portsmouth in United Kingdom. A different test, and I will try to explain the difference between these tests. The first one was just a compression test with cyclic loading, but just axial compression test. This can reproduce the state of stress which could happen in columns of buildings or in bridge piers that are compressed uniaxially. The other test is a triaxial test, which means that the load is applied not only on the axial direction, but also in the lateral surface. And this is to reproduce the state of stress of rocks, maybe around a tunnel, like in this case. So I will briefly describe the test. And this has been the results of this first test. Compression ones have been published in this paper in 2020 with Constantino, of course. And just to give you some information, we had concrete and basalt specimen. The concrete, both with the same side. The difference, of course, is in the material, because concrete is an artificial conglomerate which is made of binder, water, and aggregates. And we prepare these specimens by ourselves in the laboratory. While basalt is a very hard magmatic rock, and the specimens were cut from the quarries of the Etna volcano. In both the cases, the acoustic emissions produced by the growth of microcracks associated with fracture phenomena have been measured and then analyzed. This is how we did, just some details. We had a sensor on the specimen, and we had an output like this of the acoustic emissions. This is all the settle of the experiment. In the middle, you can see the specimen inside the hydraulic press. Here we had, with this computer, we could control the loading process. And with that one, we analyzed the output in terms of acoustic emissions. These are the load steps of in the cyclic loading. As you can see, the loads, it's always up and down, it increases and decreases, it increases and decreases until failure. As you can imagine, concrete had an average failure load much smaller than basalt, which is a very hard rock. And by means of this cycle loading, we could recognize something which is well known in the literature, which is called the Kaiser effect. That means that no cracks and no acoustic emissions, of course, can happen in before the load reaches the maximum load of the previous cycle. So this was nice to confirm again. These are the responses in terms of acoustic emissions in time of a concrete and a basalt sample. As you can see, they have different behaviors, because for concrete, the acoustic emissions started for high values, late in time, for high values of the applied load, while in basalt, they started immediately. These are the two samples, concrete on the left and basalt on the right. These are the details of the load values and the time of failure for both the specimens. And then we did some statistical analysis in terms of inter-event time, which of course is the time interval between two consecutive recordings for both basalt and concrete specimens. And this is what we got. So from the top, acoustic emissions, inter-event times, and this is the probability distribution function. As you can see, this in log-log scale can be well fitted by a power law curve, thus highlighting the complex behavior of this process. This is for concrete specimen. This is the correspondent result for basalt ones, which, as you can see, have a greater slope for the power law fitting curve. Okay, so These are the complementary cumulative distribution functions for 3 cycles of loading for the concrete and basalt sample. And you can see that, of course, from an initial saturation of at 1, then the curve show a power tail, which can be well fitted by means of a decreasing Q exponential function. This is very interesting because it shows that if we make a relation between the entropic index and the inverse of this beta parameters, which is temperature, for both the materials, you can see a different trend. Black and red are concrete ones, and green and this kind of violet are basalt ones. This means that the failure is here. So reaching the failure, approaching the failure means going like this. The value of 1 over beta Q decreases for both the materials, while the value of Q, the entropic index, is in an interval between 1.8 and 2. But the most interesting thing to notice is that the difference of trends, since while the concrete and concrete specimens approaching failure have a higher value of Q, basalt ones approaching failure have smaller value of Q. This could be explained by means of the difference, internal difference in the 2 materials, because while concrete is a composed material, so it has aggregates inside, it can show like preferential lines of fractures surrounding the aggregates. And so this phenomenon could be response of the long-range correlation quantified by increasing values of Q. On the contrary, basalt had a failure like a real explosion. And in this case, the value of Q decreased approaching failure. In this slide, we also reported the results of a previous paper by Stavrakas and other authors, which was made on a cement mortar, so white cement mortar, of course, with a very different scale because aggregates are as much smaller, but the composition is similar to the concrete one. So the trend they got is similar to the one we observed. Now I talk about the other experiments, the 3 actual ones, that where the results have been published this year in Entropy with Sergio Vinciguerra, which is the geophysicist I told about. And in this case, the materials were a sandstone called Darley-Dale sandstone, which of course is a kind of granular stone, and granite, which is very hard. So in a kind of way, it could be similar with our previous results, with a much harder material than the other. But in this case, it's very different, the test, the kind of test, because in this case, we have cylindrical specimens inside this kind of machine, where you can apply an axial force, compressive axial force, and also a lateral one of different amount. So we had pressures of 5, 10, 20, and 40 megapascal in the lateral surface of the specimen. These are the results in terms of acoustic emissions for the granite at this pressure. And as you can see, granite, like already we observed for basalt, had an abrupt increase of the acoustic emissions, which stayed almost constant, and then until failure, which is here. While for basalt, for Darley-Dale stone, we have something different because it's a more gradual amplitude in the acoustic emissions, therefore a much clearer premonitory phase, like we observed in concrete or in the other experiment. For both the materials, anyway, the failure is characterized by a peak in the acoustic emissions inter-event time here. That followed all a phase of very small ones. These are the same curves that we observed for the uniaxial process, but in this case, the lateral compression had a different role. And in this case, as you can see, the complementary cumulative probability distribution has a kind of second inflection point. So you cannot describe this curve with only one co-exponential function. This is the case of granite samples, and this is the case of Darley-Dale stone samples, but you can everywhere observe this second inflection point. And so Constantino said that it was possible to describe these new curves still in the framework of Q-statistics, taking into account two functions instead of only one. And these are the two functions. So you can see the sum of a first standard co-exponential function and a second one, which contains a further parameter, lambda, which ensures the total function vanishes. Constantino explained us that this kind of behavior is kind of rare, but occasionally it can emerge in complex systems. For example, in this case, of course, you can ask more details to Constantino about the DNA sequences of Homo sapiens. These are some details for the samples, and you can see that there are some recurrent results among the indices. And this is an analysis we did in order to see if the acoustic emissions are clustered in space. In this case, we analyzed the inter-event distance in space, and we plotted in different planes with different scales of color of blue. As you can see, these are only two examples. This is granite and this is Darley-Dale stone at the same confining pressure. And you can see that the spatial distribution is much highly clustered for granite with respect to Darley-Dale stone. So in terms of this inter-event distance, which, as I said, is just the metric distance between the spatial position of subsequent recorded acoustic events, defined like this. This is the probability distribution functions in terms of inter-event distance. And this is, in this case, I think that you call it Planck-like distribution. And it's interesting to know that the fitting parameters are independent of the time of material and on the confinement. So this shows a kind of universal behavior among these two materials. And these are the cumulative distribution probability functions of inter-event distances for both materials. And in this case, it's enough to have one single standard co-exponential function to describe all these behavior for both the stones. These are again some details, just to know that for all the tests, the sum of the entropic indices oscillates around 2. And so this is the last slide, and this shows the relation among the two entropic indices, in the one in time and the one in the distance. And you can see that all the results can be located in the area around this linear interpolation. So this means that something universal still holds for all these results. So in conclusion, pre-failure processor is in the considered materials, in particular acoustic inter-event time and inter-event distance that can be reproduced with exponential curves showing universal features. The obtained results provide an insight on the warning signs of the incipient failure of construction materials and could be therefore used in a health monitoring strategy of existing structures. So thank you all for your kind attention, and happy birthday again. Thank you. We were on the boat to Moxia in this photo.
Questions, please.
Thank you for your presentation. My question is linked with your work. I'm interested if you have some strategy in order to have a better location for sensor monitoring the health of the structure, because you don't have, we're not going to put in sensors in all structure, in particular tones or something like that. You have some strategy for that?
Of course, you can, from the numerical model of the structure, you can recognize which are the points which have more stresses. So that's the point where usually the sensors are applied. For example, in the connection between beams and columns, or in the middle of beams, just in the because it depends on the bending moment, which is the most dangerous characteristic for slender structures. Otherwise, for other structures, there are also some other kinds of tests which measure the shear forces, which I didn't mention in this, of course, in this case. Yeah, but this is with civil structures, so we don't usually take into account aeroelastic effects apart from wind structures for very high skyscrapers. Yes.
Have you looked at the correlation between the event size and the waiting time before and after this event?
You mean in terms of amplitude?
Yes, you have the amplitude and the waiting time.
Not actually. We just measured if an event occurred, and not particularly on its amplitude.
Yeah, you have a response from several different materials. My question is about the frequency response, because you just work with the amplitude, but I imagine that the frequency response from basalt is different from the concrete one. Did you do anything along that line?
Well, of course, it depends on the instruments you have. We had a very just poor set of instruments, so that's what we could measure. But of course, there could be more sophisticated setups of experiments that could measure everything else. So this is just a preliminary.
I understand that. I'm going to mention just as a comment that in looking for earthquakes. There are people in my country, in Chile, that follow up a bit along this line, because earthquakes also emit this kind of signal. And they also emit electromagnetic signal, because you see the friction and the rupture of these rocks produces the emission. So I just want to say that there is this line that this is not an isolated phenomenon, that the electromagnetic radiation could also be emitted, especially from piezoelectric materials.
Yeah, thanks. There are a lot of similarities, you're right, with the propagation of earthquakes in the soil.
So more questions? So if not, let's thank the speaker again.
Thank you
very much. So the last speaker today is Professor Welles Morgado from PUC University. Professor Welles. Energy exchanges in a damped Langevin-like system with two thermal baths and an thermal.
Não tá ligado, Ok. Tá passado. Tranquilo, vai ser mais ou menos isso. Oi. Can you hear me? Right? Okay. This one, okay. So it's a pleasure to be here again, and I don't remember the number of this reunion of the NCT, but it's a pleasure to commemorate Constantino's birthday. And I'm waiting for the next one when he'll be 90, and we will all be here. Like Morpheus said, we are still here. Right. So this work is it's an exploration of small systems and how you can affect some aspects of those small systems in order to manipulate small thermal machines. And this was done with, this one. With Eduardo, who was a postdoctoral fellow for up to the middle, up to July. And now he's at Federal University of Piauí. And the main theme would be the effects of memory in a gyrator, and then what you can do in a non-equilibrium situation when you apply a thermal bath, a work furnishing bath to that system. So okay, so these are the papers that we have been working on this subject. And there is a poster which is related by Pedro Melo in the afternoon. I hope he will be able to bring the poster, because he had a glitch on on making it at Fundão, which is quite far from here. But I think he will arrive in time. So if you want to see more details of new work, he will be presenting them. And okay, so I'll talk a little bit about what Brownian gyrators are, and how memory function and torque in the Brownian gyrators, they arise due to memory, and how we can exploit that. And then I will talk about the main theme, which is what happens when you place a system in a non-equilibrium situation by making contact with thermal baths at different temperatures. And then you apply an external Poisson noise source. And we can manipulate work and heat statistics via that Poisson noise. And we can even do some funny things with the heat flow via the external Poisson noise. So what is mainly a Brownian gyrator? It's a small 2D Brownian engine system, which is mainly a single particle gyrating around a generic potential energy minimum under the influence of friction and thermal noises. About this, all the models that I will present are in the overdamped regime, so I don't care about inertia on this case. And this was started in this paper by Reimann and I forgot the first guy name, in 2007, if I'm not wrong. Oh, we'll be seeing what is that in the following. Here it is, Filiger, that's the name. And the main idea is something is going around a minimum, okay? The particle may turn in one direction, in another direction, and how to build that. That's the idea. You can build it if you can apply different temperatures to different directions. That seems strange, but in granular systems, for instance, you can do it very easily if you apply different vibration rates in different directions. People have been doing this Rayleigh-Shaw dynamics in granular system for quite a long time. And in general, people apply vibrations in one direction and fixed walls in the other one. That already introduces a asymmetry into the temperatures. You have different temperatures according to different directions. So this is not really impossible to make. But there are other methods. Electrical methods, for instance, here is one type, which is, you can imagine a charged particle in a 2D setting, and you apply different tensions in different directions. And you can do that by connecting resistors to capacitors plates and place those resistors in different temperatures. So the fluctuations will be different. So you have different tensions, fluctuation tensions on the two directions, and that makes the system rotate. Or you can do a much smarter kind of Brownian gyrator. You put everything inside the fluid with a given temperature and you introduce some kind of asymmetry by shining some laser in a single direction or something like that. So these are the types. And what have they done? Well, here is work by Chiliberto and other people, and they did that in a different way, because here the coordinates of the gyrator are not coordinates of a particle rotating around something, but the voltage collected on those two capacitors here. And these are the signal here goes to amplifiers, and you can plot the voltage, which corresponds to the amplitude of the motion. So if you have same temperature, this is just a sphere, or if you have different temperatures, you can change it to an ellipse with axes that are skewed a little bit. And this is one way of doing it. You can observe that there are only capacitors and resistors, because if you map small circuits to mechanics, you can map exactly RLC circuits to masses and springs systems. But the capacity is mapped to the inverse of the strength constant. And the resistors, of course, are mapped to friction. But the inductors, they are mapped to inertia, to masses. So since we don't have masses here, there are no inductors here. So you don't have any inertia in this kind of problem. Another work which is similar has been done by this group. It's a more recent work. They observe in different situations. And there is another one which is more interesting, because this one was done with small particles, really, in a laser trap, an elliptical laser trap. So they induce fluctuations in temperature by inducing fluctuating electric fields, distinct electric fields in each direction. So you have the ingredients for a gyrator. They do observe the elliptical kind of characteristic. And then we are going to look at those problems, and we are going to introduce, we're going to introduce memory in there, okay? Memory function, usually they show up in a fluid when, for instance, a particle is moving there by generation of low hydrodynamic modes. Those modes, they correlate the particle with its own velocity in the past. This was, actually, this is a very old very old kind of physics, because it was found in the 60s, the late 60s, by Alden and Wainwright in the context of water. They were analyzing how a molecule of water behaves in long term. So they found out that water exhibits a behavior called caging. So water shakes around during some time in its vicinity, then it goes to the next cage and the next, etc. But that's simply a kind of exponential correlation. So that kind of exponential correlation is very nice. But after some time, water started to behave, the velocity correlation of water started to behave like a parallel. And then things were different. And this was mainly because of the generation of correlations, or for the case of Brownian particles, slow fluid motions. And we can relate, if the microscopic dynamics is known, we can relate the memory functions to the correlations of the noise itself. And this is a typical memory function that we find here. That's tau. It's a time scale for the memory. It's pretty much the time scale of correlation that correlates past and present. T prime is past, T is present. You don't have age of time. You have to introduce more things. This is a very simple model. It is. You can do that by introducing other noises, because that was exploited in glasses a long time ago, because you have this correlation of motions that has to happen, so the structure relaxes and that is beyond this simple model. This is a very simple dynamic short time model. Okay, so this is the model we looked. Here is a frictional force, no inertia, and here no inertia also means no moment of inertia. And the memory function is this one, proportional to this is a friction that comes from the memory function. And here you have a potential force, and here is the noise force. Noise force gives you two kinds of correlations. The delta, the simple local dissipation, and this one, the long-term slow modes dissipation. So this is the same that I presented before. This is a type of potential that we use, linear potential. So it's kind of easy to deal with, but we make it a little different because we introduce a factor u. So the diagonal terms are k, and the non-diagonal terms are ku. So if you have u as a scale term, if u is larger than 1 in modulus, this is non-confining potential. So the particle just go to infinity. So you don't have confination. So what happens then? We analyze the steady state. This is the correlation between the positions here. X1 is x, x2 is y for the particle. You can observe that there is a variance, non-zero variance, if you have the system like this, and well, the rest is just. This is the most important part. Since there is no moment of inertia, the total torque is zero. Like when you have zero inertia, the total force is zero. You can also do the total torque. And there are three types of torque that we can look at. The dissipative torque here, which corresponds to the friction, the memory loss and the friction mediated by slow modes. There is a harmonic forces torque. The potential does some torque also, and the thermal fluctuation torque, which is also possible. But in the original work by Finnegan and Riemann, the torque done by the thermal fluctuation forces was zero. because they did not include memory in the problem. So what happens if you include memory, if you include correlation with the past? Memory is also important because memory is also a channel where you can exchange information back from the past. You can lose information to the past and then get some of it back via the memory function. So entropy is not homogeneously, monotonically increasing. You can also have decrease of entropy after that. And this is the interesting result, because you can observe that it's a non-equilibrium situation. We need two different temperatures, otherwise you don't have this kind of torque. And of course, you need some coupling, but then you have a frictional the thermal torque appears only if you have memory, if you have a non-zero time scale. If time scale goes to zero, that means you don't have any memory. You lose the memory. Memory is only zero. Zero is that's how memory becomes to us when we get very, very old. So this is like a small effect, but it's here. And if you take tau equal to zero, then you recover the results of the previous paper. So you can kind of induce a little new physics. Yeah, going to zero, because the tau different from zero situation, you need to take into account the past. The past is important. You need to have information from the past to calculate the dynamics of the present. And so that is non-Markov in the usual definition. Okay, so those are some results. This is the average torque. Of course, all the torques, they cancel. So the particle rotates around, but it comes back. There is no systematic turning in a single direction. Oops. No. Here you have the second cumulant of the torque. Which is interesting here is that because you approach you approach 1 or -1, the inherent fluctuations of the system, they grow very, very fast because you're approaching the limit of non-confination. So the particle can just go away, and the same happens to the fourth cumulant. So it's definitely not a Gaussian distribution. So, you can also do the dynamics of the exchange of the reservoir. So you have this horrendous equation. Don't look at this, please. Just look here. You have a flux of energy. If here the energy goes from 1 to 2, of course, if T1 is larger than T2, and you can have that because of the coupling and the difference in temperature. So you have a flux between reservoirs mediated by the particle itself. And the thing is, you can really change the shape of the flux by changing the memory. So if you approach zero memory, which is pretty much the case of a Markovian system, you approach something like this. But if you introduce memory, the flux is changed. So the generation of modes in these systems can be a way of changing the heat flow of the system itself. So let's see what happens now. Oh, sorry? Yeah, the black one. The black one. No, it's more or less this one. This is, we did that just not to have divergences in the integrals and the calculation, but it's probably not, just a little bit below the black one, the black straight line. This is already because it's very simple. It goes to zero here. Should go to zero. I mean, here is zero. So this is zero flux when you have T equal to 1 equal to T2. So this is just a normal conductance kind of calculation. So, okay, so what happens now if we look at a system that is one-dimensional, but it's in contact with 3 external reservoirs, 2 thermal reservoirs and a thermal reservoir. These two are simply thermal reservoirs with temperatures T1 and T2. The idea is to keep them different, so the system is always out of equilibrium. And then we place that in contact with another source of dynamics, another source of force into the system, which will be Poisson driven. So the idea is this. This is a Langevin, a usual Langevin with mass. You can keep the mass there. And Xi1 and Xi2 are normal reservoirs, but F has these two guys here, they are internal noises. Internal noises mean if you couple the system in the two baths and have a big Hamiltonian for all of them, you can derive equations like this due to the internal dynamics of the system. But this guy here, you cannot do that for. How can you do this? You can, for instance, look at a charged particle and put the whole system inside a capacitor. So you can tune the voltage on the plate. And by tuning that, you can apply any statistics that you want, but that's an external kind of work. It's done by an external agent, a battery, a source of potential, and you can tune for different kinds of statistics. So we are going to do that when F follows a Poisson kind of statistics. For Xi1 and Xi2, they're just usual temperatures, usual Gaussian noises. But this guy is Poisson. We choose Poisson, and it has a rate lambda, and the impulse kicks are distributed according to Gaussian. It's a simple model. We can work this out quite easily. And C2n, these factors here, they have this very easy form to obtain, but you can observe that they are proportional to lambda. And these are cumulants, they're not averages. So these are cumulants. You can have cumulants of all orders. You have, in fact, by using symmetric kicks, you have all the positive cumulants different from zero and all the negative cumulants equal to zero. So it's much easier to work with. And here it is, the energy. So we can observe that the total energy is proportional to, of course, a combination of T1 and T2, which is what has to happen because this system is out of equilibrium. So it's in contact with two temperatures. And its temperature could not be T1 or T2, but some kind of combination of them. Same for the velocity. But C2 is the second cumulant of the Poisson noise. So you also have some energy that comes from the Poisson source, which is given by the third cumulant. And you also can calculate for any kind of cumulant that you want. It's gonna be if N1 plus N2 is larger than, the sum is larger than 2, of course, only the Poisson noise is going to be responsible for that. And here you have some cumulants, and you see that they all depend on the Poisson noise, because otherwise they are all zero. If you only have Gaussian noise there, it's going to be zero because you only have the second cumulant, the variance. One interesting thing is that not only this guy is zero, but all the xn minus 1g is zero for n greater than or equal to 1. That's a property which is associated with the symmetry of the velocity. Okay, so you can do the statistics for work and heat and work, and scale that by a kind of mean temperature. If you did not have Poisson, this would be the temperature of the system. And this is what we get. Averages for work, we get combination when the system is Gaussian. Okay, if you just take the lambda going to infinity and do the scaling, you only get combinations of energy and the second order cumulant of the Poisson force, which becomes a Gaussian here. But the interesting thing happens when you have Poisson, and there you have it. You start to see other terms in the average which are given here. Lambda is like a scaled Poisson rate. So you do have non-Gaussian behavior for the work and the heat. So you get clearly non-Gaussian behavior. But here is more interesting. If you look at Q1 and Q2, these are the rates of exchange of heat with the reservoir. So A and B, they are similar, okay? A is for T is 2, B is T is 2, lambda. You just increase the Poisson rate. It becomes a little more Gaussian on this side. But when you have lower temperatures, because you keep T2 constant, but you lower the temperatures, the flux does not really follow the same lines, whether you have more Poisson or less. If you have a more clear Poisson case, you invert the flux of heat. And this is seen here. Usually Q1 is, one of them is positive, the other one is negative. Q1 is negative because, I mean, Q1 is positive because the system is getting more heat from Q1, and Q2 is negative because it's rejecting heat on Q2. But there is a change in that. If you increase the Poisson rate, it becomes the sign changes become positive, and here too you can work with these two parameters. This one is more related to friction, but if you look at the Poisson rate, you can change the flux of heat, which is quite strange. But it's easy to think if you input too much heat in a system. For instance, T1 has a larger temperature than T2. There is a tendency for heat to go from T1 to T2. But if you do so much work via the F on the system, you heat it up so much that it can start to give heat to both reservoirs. So you can manipulate the flux on the reservoir by doing this. So then that's why you get the same sign for the heat. Okay, so that's the summary. We have exploited the role of memory and non-standard forces. Memory, for instance, allows new forces, new torques to act upon the gyrators, for instance. And of course, memory is also a channel to recover order lost to the thermal bath. And by mixing usual thermal baths and a thermal reservoirs, you can also alter the work in the heat statistics. So including changing the direction of heat in those systems. So this seems to show to us that manipulating these systems with that kind of buttons, you can kind of control it better. You can use it to do machines. That's the next step, of course. And I'll stop here. And I thank you very much. And happy birthday again. And we hope to see you again and everybody here when it's 90. So.
Questions? No questions?
Well, thank you. We can imagine also a situation where work is done, strongly work, so you can take heat from both, it absorbs heat from the top and make a lot of work, no?
That's a more difficult situation because here the system is a kind of situation where you can input energy. It's kind of It reminds me of an example with billiard balls. If you put a billiard ball in a channel in a channel 1D channel, and you shake it up so that the ball kicks on the bottom. If you do that, you are pretty much always inputting energy to the system. In order to take energy out, you have to kind of correlate the kicks with the motion of the ball. You have to do some kind of feedback. If you introduce some feedback here, if you measure the velocity of the ball, if you measure the velocity here of the particle, and you apply a force that does negative work, you could do that. But you have to introduce a new feature to this problem. You have to introduce some kind of feedback. You have to do a measurement to see what is the velocity of the ball, and then you apply a counter force. So you kind of reduce the velocity instantaneously. That could be possible, but you have to introduce that. You need information to do that. Without information, what you get is you introduce heat to the system, and you throw the heat to the reservoirs. But if you introduce feedback, you can do that.
Okay, let's thank the speaker again. So, Fernando, I think it's better you explain again. There will be this shift. Maybe some people are not here when you.
Hello. This afternoon, we'll merge the coffee break with this second poster session. So everything will be shifted by 30 minutes. We will start this session. We will start at 15:30. Understand that? These two, we will see posters and drink coffee at the same time.
Yes. So I am deeply indebted to Constantino. Constantino has changed my life substantially because it was Constantino who brought me to Brazil. I met him 86 in Montreal at the conference on magnetism. And I told him, he told me, oh, come to Brazil, visit me. And so he visited me, I visited him for 1 week. And I was enthusiastic about Brazil. And so he said, why don't you come back for a year? We'll try with the Guggenheim Foundation Fellowship. And he was the one who proposed me to this fellowship, and it worked. And so the next year was 87, and I came here for 1 year to CBPF and spent a wonderful year. I always say this was the best year of my life here in CBPF, and from there on, my relation to Brazil became very solid, and now I'm living here. So thank you very much, Constantino, already for this wonderful start. But I came here, and what I did here was to work on a model on a model. Oh, this is even stuck. Sorry. Stuck here. Got it. Well, hopefully works now. Not. Sorry, it's a little complicated. Again. So I hope it works now. No, it does not work. Yeah. So we work on nothing less than the origin of life. In fact, Constantino and Ricardo Ferreira, they had done a fundamental work on biogenesis, on the question of how, from the primordial soup, one could get DNA chains. And my task was to simulate this. And indeed, we found that there were these chains of amino acids, the oligomer soup, which slowly created these long chains. And there was a critical point at which you could calculate actually very well the size of these chains. So this work was actually even, was an article in Folha de São Paulo about this article. I didn't find this article anymore because there was a photo in Folha de São Paulo of Constantino standing in front of the supercomputer. But at that time, Constantino never touched the computer. Anyway, I spent a wonderful time. At that time, there was no Q statistics. This was before the Q statistics. But nevertheless, there was huge activity here. I mean, Constantino had many students, and there were a lot of people here making PhDs, and Constantino was full of ideas, running around faster than today. I mean, you can imagine how it was. It was very fast. And the big subject at that time was the thermal transmittivity, or called the collapse, or this break collapse method, which was a beautiful trick it had used in real space normalization to facilitate the calculation of the graphs. And later there was something even more beautiful, namely that due to this very wicked transmittivity, it was possible to obtain the critical point exactly. It was always a duality relation that was fulfilled. So this technique was extremely powerful. And Constantino produced, I counted, it was 100 papers, at least a little bit more than 100 papers in this context. He applied it to many, many models. And in fact, he had a lot of students at that time. I will show maybe a picture of the students here. And there's all these people that you are seeing here, Luciano, Conceição, Ananias, there was Anna, there was, Edson, and then there was also, of course, Sergio and Marcelo and Fernando and Daniel. All these people were working on things related either to this normalization group stuff, which, as you might remember, produced big departments of statistical physics in Maceió, in Natal, in Cordoba, everywhere. Constantino was able to create statistical physics groups with this, with his students that were all formed. I mean, it was really a big impact on Latin America. And besides this break collapse method, which of course was very prolific, there were also, Constantino was very, very broad. He had many other things at the same time. It was not just corte collapso. So he had, for instance, Conceição working on chaos, of course, a route to chaos. It was sorry, it doesn't work very well. So chaos, route to chaos. It was a beautiful work in which Constantino invented a gap in the Feigenbaum mapping, and this gap produced also funny things. And then other work which he did, which at that time was working with Hellman and with Antonio on the fractal properties of polymers. It was another, at that time also Lucilla and Cornelio were here. This was a very active time. And other things that he worked on was, for instance, with Daniel was neural networks. And then he also worked on population dynamics later on. And so he was extremely broad, yeah? And then also worked on stock exchange. So Constantino had many activities before this Q statistics. And then I will now tell you what happened. So, no. And he was actually what he liked the most, what his most favorite, let's say, activity was to generalize. He liked to generalize. And we called him, I mean, I don't know if you know that, we called him the generalizer. Yeah. And you can see all over, he generalized the TJ model, he generalized the Hubbard model, he generalized the Archie's law, he generalized the slip dynamics, everything he generalized. And so in 87, when I came, of course, I gave a seminar. Everybody gives a seminar. And at that time, I brought the subject to Brazil, which actually was new. I think it was the first seminar about subject in Brazil, which was about multifractals. So I gave a seminar about the work of Henschel and Procaccia, about the generalized dimensions. And so Constantino was very happy. Oh, generalized dimensions. He liked that a lot. Yes. And then after the seminar, Constantino said to me, come in my office, explain to me again, how was this Q going to one limit? And I went to the backboard and I repeated more or less what I knew. So I wrote this story here, could go into one, you have this limes here, you see, you have this expression, then you can do the exponential on top, and you can develop the exponential, and then you blah, 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 and you get this what? You get this entropy. And then Constantino, oh, interesting, beautiful, again, entropy. And then we left to Maceió, the conference, and while everybody was playing soccer, Constantino called Evaldo and me to the blackboard and said, I have an idea. What about if we turn everything around? And instead of having a generalized dimension, we have a generalized entropy. We use this now for different Qs than Q equals 1. And Evaldo and myself, we looked at each other and said, wow, he's getting nuts, ne? So we were like scared a little bit, ne? And then Constantino had to travel. He went, I don't know where he went. On the plane, he wrote his paper. And when he came back, he wrote his very famous work. I mean, first he explained on the blackboard. This is not that was in 83 in Belém, but then he looked like this. This was the shape of Constantino. He was very young and very slim. And so at the end, he wrote this famous paper, which today in Google Scholar has 11,000 citations, and which actually in Journal of Statistical Physics, that you see, is now by far the most cited paper. You see, this is now from a Web of Science. It is the first paper on the list of the papers of Journal of Statistical Physics with 6,800 citations. The second one is the one by Feigenbaum. So in fact, Leibowitz has to give you a prize for having, yeah, I think you should tell him that he owes you a prize for making his journal famous. Yeah, so yes. So this was a big, I don't need to say much more about the importance of this work. I mean, everybody has heard about this. Many people have worked on this here. And in fact, you know, I mean, Constantino, big thing, he generalized Boltzmann, and this came to, I mean, I don't need to say how important this work was. We have now nearly 10,000 papers written on the subject. It's 9,900 and something papers, so it's a huge amount of papers. There's nothing similar to this phenomenon. It's an amazing phenomenon that we are watching, and there are, of course, there were many people that were jealous and furious. So there were a lot of enemies, no? And Constantino had to spend a lot of energy fighting, but I was extremely admiring him because I would not have survived this war. I needed a lot of let's say, and Constantino never owed anybody an answer. He always had the answer, always could respond to every attack. And you see who attacked him were not anybody, were all the big shots. Constantino was never afraid of facing the big shots. There was also not only Greek warrior, but also a lot of Argentinian self-esteem behind that you need to survive this kind of war. So I really admire you. For 10 years, he was really in big trouble at the beginning. And nowadays, it's, he have won. I mean, these people, some of them are dead, and some of them are, and some of them have shut up now. I mean, this was, yeah, so really, congratulations, Constantino. This was a heroic act. I mean, to show that you are a very strong person to fight back. So this is the story of this field, and of course, nowadays we have beautiful books about it, not just only written by Constantino. These are beautiful things that he wrote now. And then also we have a bunch of other books by other authors, even applications, you know, the applications in hydrogen physics and astrophysics. And there even a book about, sorry. Oh, it's a different direction. No, there's even a book on water engineering, application of water engineering. We have seen today application in civil engineering. We've seen, I mean, so this has been really, in every field, has been an impact. And well, I don't need to say more about this field because I guess that you are going to talk about this also, about this huge statistics. So this is so far about the let's say, the scientific part that I have watched him going. And now I would like to say some words about Constantino's life. So Constantino was born on the 5th of November, 43, yes, so on Sunday was his birthday, and in Greece, in Athens. And then he went with his family at 4 to Argentina, to Mendoza. You have some beautiful pictures. He was still in Greece with his father, Emmanuel. He was Mother Cleopatra and his two brother and sister. And here you have some photos. Here he is again, here and here, with his family in Mendoza. So there, of course, he spent his first years, and then he went to Bariloche to study first chemical engineering for 2 years. But in Bariloche, evidently, he had a lot of fun, as you can see. He had parties. It was a nice time, as far as I can judge. Here he is with his mother, Cleopatra. So he spent a few years in Bariloche, and then he went over to physics, where he met Guido Beck. Guido Beck was somebody that had worked with Heisenberg, and that he had to leave Europe because he was Jewish and was persecuted. So he went to Brazil. He also went to Argentina and then back to Brazil. So my feeling is that his trajectory also inspired later Constantino to go to Brazil and so on. So Guido Beck was a very, very famous and very important person. And under his guidance, Constantino made his master, his diploma. And then after that, he got a scholarship to go to France. So here you see Guido Beck. Yeah, Beck, yeah. And in France, he made his PhD. He got a scholarship. He made his PhD relatively freely in Orsay, in Saclay, in SRM. There was André Guigné, who somehow a little bit survived, so looked at what he did, but actually he was completely alone and free in his PhD. And at the end, when he then defended his PhD, André Guigné was completely marveled about his answers and answered, Monsieur Tsallis a du flair. Il devine la réponse. He knows already the answer before you ask the question, kind of. So it must have been a very impressive exam. Actually, he had, of course, surrounded by very important people at that time. There was Bocara, Nino Bocara, there was Sarma, there also Desgen. So all these people inspired him at his early ages. And at that time, he was a pure solid state physicist. He did a lot of work, mostly alone. He was very, I show you some papers. So here, this is on ferroelectrics, and here this is on spin orbit scatterings, and this is here about bosons. So he worked, you see, this was still in resonance magnétique. This was where he worked, what is his PhD. And then he went, well, I will tell you in a minute, he went so he actually was teaching, he was having his PhD in Saclay, and he was teaching at École Supérieure de Physique et Chimie, which is the place at which Marie Curie also worked, and Desgennes and Langevin and all these people. And then in 75, I guess also under influence of Christina, they decided to leave France. He had a permanent job. He was a maître de conférence, so again, a very courageous decision to leave a permanent job and to go back to South America. And there he went to Brasilia in 75, where he worked for 2 years. And I showed you here also some papers he wrote at that time. This was already in Brasilia. And then 2 years later, he went to CBPF, where he is still today. Everybody knows CBPF. And in CBPF, he, of course, established himself, became very, very influential. And I show you here a typical situation. So here, this was at the 60th anniversary of the CBPF. You see here Nussenzweig. You see here is Macarenas. You see here, this is Galvão. Here you see Sergio Rezende. So all the big shots of the Brazilian establishment in physics surround Constantino here at the CBPF. And of course, Constantino is also in the Northeast very well known, and he every friend of everybody, as has been mentioned many times also in this meeting. I mean, Constantino is extremely easy making friends, so he has many friends all over, and even his enemies at the end become his friends. So I mean, he has a lot of let's say charm, and so yes, here I show you some more friends. So Salinas, Mauricio Coutinho, and Cesar Sabareto, all his friends. And so he's now fully, let's say, one of the big shots of the Brazilian establishment. He also, here I show you some more pictures. So here you see him with Stanley, with Stauffer, with Luciano, who unfortunately is not anymore here, and myself. And then he, of course, is internationally very well connected. He has many friends also internationally, all over. So here you see him with Cohen, yes, with Cohen, and here you see him with Kawasaki, this great friend of his, and here with this guy is never changing. Alessandro, no? It looks like all the same, the same guy, yeah. And this is here Michael Fischer, who also is gone now, and his wife that was from Spain, and Stanley, yes. So all these people. Yes, they are his friends, and actually he is also a friend of more important people. He's even a friend of Nobel Prize winners. So here with his friend Gell-Mann, with whom he had a bunch of papers, actually. And also these triple Qs was invented with Gell-Mann. And here with Toft. Oh my God, I don't know why this always runs away. Oh my God, sorry. Here with Toft, we had visited Brazil, Rio, and this is at the Cristo Redentor. So you see, Constantino is always well connected all over. Constantino had also made many contributions to the society, to the organization of science. So not only, as everybody mentioned, he founded our ENCT, which we are now. I mean, he's the creator of this community, and he's also was also for many years the chief editor of Physica A, and now it's honorary editor of Physica A. But there's a long list of achievements that he had. He was a Guggenheim Fellow, of course, and he organized StatFis in '89. He was the head of the department here in CBPF for a while. He was involved in Santa Fe Institute. He is still involved in the Vienna, in this complexity hub. He is professor at the University of Catania and member of various academies of science in Brazil, the one here of economy and political sciences, and in Latin America. Yes, and he also is very engaged in popularizing science. So here you see him in this Itacoatiara, which I've never seen this place before. Itacoatiara, he was there to teach the Indians from the real India, from India, not from India, from the Indians. He teach them physics. Yes, and then Constantino also has a very rich family life. He's has a first family with Maria Cristina. You see here his son Adrian, his daughter Alessandra, that are here. I mean, Alessandra is here, and Alessandra is here. And then he has a second family with Maria Aparecida. He was a great father. All his children like him very much. Here you see him with his son Emmanuel in Santa Fe. And so he of course, he has a very nice life now. And his third family with Marisa, you see he looks very happy. And then, of course, he has his children and his grandchildren. So children I've already shown you here. This is here in Brasilia when he got the prize of the Commandator, whatever. We'll come into this later. So here you see Emmanuel and Adrian and Alessandra, and they have also children now. So he has but this, I took some pictures now, also the recent ones. I thought, I mean, you cannot show children as children, have to show big people. So he is a successful sales manager, he is a successful economist, and she is a professor. So all of them are now established people and are all proud. He's very proud of his children. Eh? And then, of course, he has also grandchildren. Yes, here you see, this is Flora, but she was now, he's somewhere here. I've seen her somewhere. She's sitting there. She goes, no, this was about 10 years ago, more than that. Here's Enzo, whom I never met. And there are more grandchildren that I've never seen. That one day I have to make a photo of these grandchildren also. Yes. So Constantino has, of course, also got many important awards in his life, many important honors. And I would like to show some of them. So he became Comendador da Ordem Nacional do Mérito Científico here in Brasilia, which is the highest order you can actually get. And you can see here in the back, somebody that you recognize. It's Jose Ignacio, he was there also present. And so this was, of course, very important for science. And then he also got another, even more important prize, the most important prize in science in all Latin America, which is in Mexico, the prize for science and technology given personally by the president of Mexico, Mr. Vicente Fox. And then he got also another very prestigious prize in Athens, from the Academy of Athens, which is actually very, very, very old, because it was founded already in the 5th century before Christ by Plato, and has this huge tradition. And he was awarded the Aristio, which is the Excellence Award. So this is a really historical prize, a very important prize. And so you see, I mean, you cannot get better. And you soon, of course, now since Celia is in the committee, we have to get the Bolton Medal also. We'll see. Anyway, and then he got the Elsevier Prize, and actually he got even the prize in Disneyland. For the best show. Yeah. It's on the left. It's on the left. Yes. So he also has various honorary doctor degrees. So he got a doctor honoris causa in Salonika, in another city in Greece, which is the university, or another big university in Greece. Then he got a honoris causa in Cordoba, where I already told you he left behind an entire department of statistical physics. I mean, really created this. Then he got another doctor honoris causa here in Brazil, in Maringá. And finally, of course, also in Natal, which is another department in which he had a huge influence, because I mean, there are many here actually who are professors in Natal, already even in the emeritus, but I mean, it shows how long ago he had this huge impact in Natal. So yes, this was in Natal. So I now come soon to the end. I had with Constantino a long-lasting friendship since. We have met many times in many places, either here or somewhere else. This was in Mexico, but we have been in Este. I remember when you had to, for the first time, present the Q statistics in Este, there were all these sharks around, and it was attacked from all sides. You remember, Mandelbrot was there, and Pietronero, and Stanley, and Aharoni, and all these guys. It was really tough. So we had seen many situations, and I mean, we have finally really made a good friendship. I would like to thank you very much for this friendship, and I hope that it will go on forever. I mean, this is really great. So I wish you a happy birthday for your 80th, and in particular, I wish that you have many, many more happy years. This was in Bali, I guess, picture. And so thank you very much for everything. And now I would like to show you some contributions of other people. So the first one will be from Ángel Plastino. So Ángel Plastino, yes, he sent the following video.
On this momentous occasion of Constantino's 80th birthday, I'm filled with a deep sense of gratitude and admiration for his incredible achievements, both in life and in science. His contributions to physics have been extraordinary, and they have launched countless scientific lives. I am reminded of the many qualities that make Tsallis not only a brilliant scientist, but also a cherished friend. His work dedication, his insatiable curiosity, and his commitment to knowledge have been an inspiration to all who have had the privilege of knowing him. His impact reaches far beyond the laboratory or the lecture hall. He has been a mentor, a guide, and a source of wisdom to many people. His willingness to share knowledge, his kindness, and his enthusiasm have left an indelible mark on all of us. But it is not just his scientific achievements that we celebrate today. We also celebrate the warmth and humor he brings to our lives, the memories we created, and the friendship that he has sustained us through the years. On behalf of all of us, I want to offer my warmest wishes for his 80th birthday. May his days continue to be filled with joy and new discoveries. Feliz cumpleaños, Constantino.
Now I would like to show a movie by Galvão, who was former director of CBPF, and he was director of Este, now director.
Amigos do CBPF, colegas da comunidade científica, alunos de graduação, de pós-graduação e outros colegas presentes a essa cerimônia. Lamento profundamente não poder estar presente presencialmente neste evento de comemoração de 80 anos de Constantino Tsallis, 80 anos de uma vida altamente produtiva. No final da década de 70, tomei conhecimento do trabalho de Tsallis e me interessei muito pela possibilidade de aplicá-lo em física de plasmas, um sistema que, como todos sabemos, bastante complexo. Em meados da década de 90, comecei a aprofundar-me mais sobre as ideias do Constantino e logo após tive a felicidade de ser apresentado a ele por um grande amigo comum, Aldo Kraevich, que infelizmente já nos deixou. O Aldo veio à minha sala e disse: Galvão, tu tens que ir ao seminário do Constantino que vai ser agora apresentado. Eu fui e me encantei com o seminário. Fiquei impressionado pela clareza das ideias do Constantino e pelas possibilidades de sua aplicação. Logo após o seminário, conversamos e o Constantino interessou-se, inclusive, de fazermos um experimento em física de plasma para testar suas ideias. Infelizmente não foi possível fazê-la, mas, logo após, na Universidade de San Diego, fizeram experimentos numa máquina confinando plasma só de elétrons que mostraram alguns aspectos bastante relevantes de aplicação da teoria de Tsallis a plasmas confinados. Mas foi quando eu me tornei diretor do CBPF que eu vim a conhecer Tsallis mais profundamente. Nos tornamos grandes amigos. Eu tinha enorme satisfação de ir à sala dele e conversar sobre problemas que extrapolavam a mecânica estatística. Aprendi muito com ele e comecei a admirar sua maneira de encarar problemas de uma forma prospectiva, sem se preocupar com aquilo que já está consolidado. Ele não tinha medo de fazer perguntas, não tinha medo de argumentar. Isso foi muito importante, inclusive, usando parte das conversas que tive com ele, pude orientar um aluno de doutorado, que hoje trabalha na Escola Politécnica em Lausanne, sobre a aplicação da entropia não extensiva para transporte em física de plasmas, aliás, melhor transporte em plasmas magnetizados. Eu me lembro sempre, no final do ano, quando tínhamos aquele evento em que cada coordenação apresentava seus principais resultados. Constantino fazia questão de ficar desde o início até o final, sempre fazendo perguntas bastante incisivas, bastante construtivas. Isso dava uma demonstração clara, não somente do seu interesse pela física em geral, mas também a sua grande dedicação ao CBPF. Constantino, todos nós físicos brasileiros, em particular aqueles que trabalham e trabalharam no CBPF, te agradecemos muito por tudo que fizeste pela ciência brasileira, tudo que fizeste pela física brasileira e por tudo que ensinastes, não somente a alunos, mas a colegas como eu. Um abraço fraterno, Constantino.
Well, now we have some small depoimentos from his children. Maybe you can start while we install Adriana, porque Adriana has a computer, and we need to zoom it. We need to zoom it, and this is not so easy. No. No presentation. No. You talk. Okay. Yeah. No. Okay. So Adriana will start. Yeah. Yes. I will turn this down.
Okay. Good afternoon, ladies and gentlemen. My name is Adrian Tsallis, and as you can guess by the name, I am one of Constantino's son, together with Alexandra and Emmanuel, who are also in the room. Okay, let's breathe a little bit, right? Okay. First of all, I'd like to apologize for this session not being on the event schedule, but Since it was supposed to be a surprise, you can agree that it would be very hard to hide from my father if my name was over there. Okay. Anyways, even though I am very emotional, obviously, and I'm very far from the, I'm sure I will only take 2 hours, but I'll get there, okay? I'm very far from the academic world. So I thought this would be a great opportunity to share some things I learned from my dad along the years that can be applied both to science and to life in general. So our guest today, I will be proposing the generalized Tsallis rules of life. Okay. Okay, no, don't worry. Okay, I'll get there. I'll get there. Okay, I thought this would happen by the last line, not the first. Okay, so let's see if this helps. Okay, let's see if this helps. Okay, let me walk a little bit. So I'll be proposing the generalized Tsallis rules of life. So I promise 2 things. First, I will not be showing any formulas or mathematical equations. And the second is this lecture will be way easier to follow than the previous ones, that's for sure. So let's cut to the chase and let me tell you a few stories of the 5 things I learned by being Constantino's son. At a very young age, we all hear from our parents that they are raising us to be better than they are, right? Everybody. I raise my kids telling them, I want you to be better than me. Well, I always heard that, but from my point of view, I had in front of me a person who could write a bunch of letters together and do math with them. And he could also speak 6 different languages. And if that wasn't enough, he speaks them natively. Okay, I can't complain. He made his part in our home. We spoke Spanish. So as a Brazilian, I am both a native speaker in Portuguese and Spanish. So I only have 4 more languages to go. Great. Now we have page missing. Oh no, okay. That would be great. Beside all the jokes, as a kid, I always saw my dad doing mainly 3 things. Traveling the world to participate in physics events like this one, working on some physics papers to get published, or he would be telling us about a crazy discovery he was able to do using something that he explained, but we never really understood. We just nodded. So sorry, Dad. The thing is, he did all of this with a level of enthusiasm that you could feel in the air. I can't really remember any of the explanations nor the discoveries he made, but for sure I can remember his enthusiasm. I should never have done this, Hans. Thanks for the torture. Okay, well, that made me learn about passion and how it can be a great source of energy to achieve any goals you want. As I was saying, normally his explanations included showing us graphics or formulas and telling us, see this curve, it's a natural event. And these dots, they represent the previous way to analyze them. And these other dots, they show the same analysis, but using the equation I developed. Okay. The curious part is that he would always use the word beautiful in those explanations, as if beauty was a science variable. See how this curve is prettier than this one. See how this equation looks prettier if we put a certain letter here. It looks more balanced. It was as he was talking about aesthetics and not physics. And this taught me that the best solutions for any problems always has beauty attached to it. You just have to look at it the right way, and it's your duty to find it. Another thing I can remember very well is that he was always talking about discoveries and applications in various subjects as literature, cardiology, galaxy studies, stars behaviors, politics, and so forth. And I go back to the feeling of enthusiasm. You could feel that he was more passionate by the process of discovering than by the discovery itself. It felt like he was opening a gift, and inside there were 2 new gifts. And that made him love to open the gifts just to see what he could find inside. And that taught me that the power of curiosity and how it can lead to a lifelong learning life. After all, we always have 3 types of knowledge. Everything that we know, like I know how to drive a car, I know how to ride a bicycle. There's also things that I know that I don't know, like how to build a rocket or how to fight a plane. And lastly, there is a world of things that we don't know that we don't know. And curiosity is the passion to explore this part of the universe. And my dad showed me that this is where the very interesting things in life are. Okay? You're getting the message, right? Okay, bro. Okay. You have a liter of what? Okay. That's much better. Okay, so let me see. Okay, so that's where the interesting things in life are. And this is intricately connected with the next thing I learned, which is to trust your instincts. I can remember clearly one time when we were having dinner and he told us something like this. Guys, you will not believe it. I just received the results from the Voyager spatial rocket, which is 46 years away from Earth, and my prediction was right. A set of scientific particles behave as I predicted, or it was something like that. Dinners were always fun with my dad. But in fact, he was teaching us that sometimes the volume of data is so big and there are so many variables that you don't control, that you have to access something that we all share as humans. And that allows you to see patterns, even if you can't rationally understand them or see them. You feel them. Is that feeling you get that makes the hair on the back of your neck stand? Although you can't prove it, somehow it shows to have great scientific potential, and my father is the living proof. Sometimes the only proof you have available is that it feels right and it looks beautiful. And so we come to the last lesson, which is resilience. Thanks God. I remember countless times to see my dad angry and mad because some editor wouldn't approve one of his papers without a reasonable reason. The editor simply did not like his entropy and therefore wouldn't publish anything that was related to it. The impressive thing is that on the following day, he would work harder. He would improve even more the paper. Many times, the unreasonable denial made him stronger, better. And that, for me, is resilience. is the ability to keep going forward no matter what comes your way, as Hans showed on some hard battles he have had. So that all makes me think that one of the great achievements one can aim in life is to impact the biography of others and to make a difference in the world. That done through science is way more difficult because most people don't see science as something sexy. So in order to mobilize someone in a specific direction, you have to be truly captivating and intriguing at the same time, so that you can reach the depths of the person's heart. I promise I'm close to the end. All of your more than 450 papers, 25,000 citations, dozens of master's and doctor's degrees you oriented are a living proof you have done very well. You are an original science influencer that many TikTok influencers would be jealous. It is a privilege to have you as my father. This is the part I thought I would die. And I'm sure your parents are very proud of you. Thank you as your son and as a citizen of the world. Happy 80th birthday. Let me get rid of this.
Thank you, Adrian. Thank you very much. I give no the word.
Eu não sou tão ingênua quanto meu irmão, porque eu sou acadêmica, e como eu já sabia que seria muito difícil falar, eu escrevi uma frase bem curtinha, porque entendo que essa frase ela expressa um bocado do que a gente viveu. Eu vou falar ela em português e o Emanuel vai ler ela em inglês. Eu escolhi começar falando ela em português porque meu pai nos ensinou uma coisa. Foi aqui que ele desenvolveu ciência. E é aqui que ele acredita as alianças para fazer tudo o que ele fez. Ele é um grego que estudou na Argentina, que estudou na França, mas ele escolheu o Brasil. Escolher o Brasil significa fazer dessa aliança uma aliança de coração. Por isso, então, eu escolhi o português para falar, ainda sabendo que essa língua não resolve para todos, mas nós somos uma família, filha de um grego, de uma argentina, de uma brasileira, temos uma francesa, um brasileiro e um americano. E juntos, meu irmão diz que vamos dominar o mundo, porque parece, né? Uma Liga da Justiça. Feita essa introdução, eu e o Adrian, a gente não se falou sobre isso. Eu não li o que ele escreveu, nem ele sabe o que eu vou ler agora. E isso significa uma prova científica. Eu, que sou psicóloga, posso atestar que as lições que ele disse que aprendeu com meu pai são verdadeiras lições que foram dadas por ele, porque eu e Emanuel também aprendemos as mesmas. Fazer ciência é um trabalho que está diretamente relacionado à capacidade de sonhar. Sonhar para entender, sonhar para ter coragem de fazer perguntas, sonhar para construir um mundo melhor. Para tudo isso, é preciso ser curioso e criativo. Nós três podemos aprender isso em casa, com alguém que nos ensina até hoje, através da paixão, isso faz entender de verdade o que é viver uma vida inteira. Muchas gracias, Pablo.
So now I have the burden of speaking the same sentence in English. So here we go. Making science is a job differently related to the ability to dream. Dream to understand, dream to be brave and ask questions. Dream to build a better world, and for that we must be creative. The three of us had the chance to learn it at home from someone who continues to teach us through passion. That truly shows what it is to live a full life wholeheartedly. Thank you very much.
I didn't know about that. I didn't know that they were preparing all this. Well, it's not very interesting to present what I prepared. And now, after all this, and after... Esse aqui. Isso. It's a very hard task to talk after what Hans said and after what Adrian, Cleopatra, Alexandra, Cleopatra, and Emmanuel said. I will never find words to thank the organizers of this event, Evaldo, Fernando, and Hans, and I will never find words to thank Hans, all he generously said about my life, and needless to say that I will never find words to thank Adrian, Alexandra, and Emmanuel what they said. But overall, I will never find words to thank the most important of it, which is your presence here in this occasion. Well, I put a title there, and then I thought half a century life resumed in 1 hour, it's impossible. So I selected as a topic to talk about Q statistics and the non-additive entropies. But many of the ideas that I will mentioned are applicable to my entire activity in science, but in fact, it is applicable to the activity in science of all scientists in the world. They all, in some level, they have the same feelings, the same temptations, the same doubts. But let me start with this little table. And here you have the famous expression of entropy that Boltzmann and Gibbs introduced in physics 150 years ago. And here you have the expression I will be talking about, that I first thought of it in 1985 in Mexico, but then I published 3 years later in 88. And it took me 3 years to decide to publish it because I liked some form of beauty that this expression had, but I didn't know what is it good for. So I was not publishing it. And after 3 years, and after a particular discussion that we had in Maceió with Hans and Evaldo, coming back to Rio in the airplane because there were too many moustiques in Maceió, then I calculated the optimization of this entropy, and I found the Q exponential, which I found it very cute, because I said it's funny. In one limit, it is exponential, and in another limit, it is a power law. These two laws in mathematics are very, very important and very universal. They appear everywhere. And they were both in a unique formula. So coming back to Rio de Janeiro, I decided to publish this idea. I would like to mention that there is something very important for me, that the expressions Tsallis entropy and Tsallis statistics were introduced in the scientific literature by two ex-former students of mine. So the expression Tsallis entropy was first published by Ananias, who is there, and the expression Tsallis statistics was published for the first time by Anna Shame, who is there. And we had a short discussion with Anna whether the names are important or not, and we concluded that they are important. And this is why I am particularly touched by the fact that these two expressions that appear very currently in the literature were introduced by young people that were introduced in science by me. So thank you, Ananias, and thank you, Anna. Then I would like, among the thousands of papers that Hans mentioned, I selected this one for a variety of reasons. So that one is by Plastino father and Plastino son, who is here, because this paper was the first physical application of the Q entropy. So during 3 years, I didn't want to publish that because I didn't know what is it good for. And this is the first paper in which they showed that it is good for something. There is another reason for having selected this. It's because Angel Plastino father was coming, but at the last time he canceled his coming to Rio de Janeiro because his wife, Graciela, the mother of Angel Plastino Jr., was not feeling very well, and he didn't want to let her alone at home. And there is still another reason for which I selected that one, because when I received this paper, I was in Florianopolis in a workshop together with Roger Menard, a great friend of mine who unfortunately left us already. And we discussed with Roger not less than 4 hours, going near the sea, the beach, and coming back, etc., trying to understand why this Q entropy is useful for understanding an astronomical system, which are the stellar polytropes. Why? And after talking 4 hours about this, we concluded correctly that it is because gravitation is a long-range interaction. And this was the heart of the reason for which this strange entropy was useful. Here you have some formulas, but I would like to mention 2 words, additivity and extensivity. And these 2 words involve addition, sum. And because the 2 of them involve sum, they are very frequently confused in the mind of thousands of people, which do not distinguish very clearly between this word and this word, because it's basically like summing something. So additivity, defined by Oliver Penrose, who is the brother of Roger Penrose, the Nobel Prize in Physics, in his book 1970, Foundations of Statistical Mechanics, he says that an entropy is additive if for 2 probabilistically independent systems A and B, the entropy of the sum equals the sum of the entropies. But SQ satisfies this, and therefore it is non-additive, because it has an extra term here, which reminds a little bit of quantum mechanics. This is additivity. So if you have a new expression for an entropic functional, it will take you only 15 minutes, if you know a little bit of mathematics, to find out whether it is additive or non-additive. So it's very simple. Extensivity is something very different. Extensivity has to do with thermodynamics, and it has to do that with an entropy, a particular entropy for a particular system is proportional to the size of the system or not, whether it is extensive or not. So this is basically the reason for which nutritionists tell you if you eat a steak of 100 calories and an ice cream of 100, another 100 calories, then you have put inside 200 calories, the sum, 100 plus 100. So it's related to this. To understand the difference of extensivity and entropy, nothing better than an example. So if we have a system in which the total amount of microscopic configurations increases exponentially with n, for example, n coins increases like 2 power n, the number of possibilities. You must use Boltzmann entropy because it is the logarithm of this, and the logarithm of this is proportional to n, and that's fine for thermodynamics. But if you have a complex system in which the number of possibilities is smaller, much smaller than this, something like a power of n, and not an exponential of n, then if you use Boltzmann entropy here, the logarithm of this is proportional to the logarithm of n, and we don't want logarithm of n. We want n for satisfying thermodynamics. So it doesn't work. But if you use SQ for a specific value of Q, which is this little expression, where rho is the same rho that is here, that is proportional to n, and that's okay. But of course, this is a mathematical possibility, this is another mathematical possibility, and there is a trillion of mathematical possibilities, for example, this one. And for this one, there is no value of Q that is correct. So you must use a different entropy that I will call S delta. If W is a logarithm of n, you need a different entropy. And when I had these three, 1, 2, 3, it came to my mind, but the logarithm is important. So what is the entropy associated to the logarithm? So I went to the office of Evaldo, and I asked him, what would be the entropy if we have a logarithm here? And he said, let me think, I will tell you. And a couple of days later, he told me, he said, I found it, it's that one. And if you have this family, it is proportional to n. So you see, okay, 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 and okay, because they are proportional to n, 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 n. And this brings me to this table. Boltzmann entropy is additive. SQ is non-additive. S delta is non-additive. And that entropy of Evaldo is non-additive. But if you have this type of system, you should use that one because it is extensive. And you should not use this, or this. If you have this expression, you should use that one. If you have this expression, that one. And if you have this expression, that one. So, if you married Boltzmann, you will stay here until the death separates you. But there is a better marriage, to marry Clausius or thermodynamics, and you will stay here until the death separates you. But why is it interesting to stay here? For many reasons, but let me show to you that we are in good company in that diagonal. Because Einstein, in 1949, he wrote A theory is the more impressive, the greater the simplicity of its premises is, the more different kinds of things it relates, and the more extended is its area of applicability. Therefore, the deep impression that classical thermodynamics made upon me, it is the only physical theory that will never be overthrown. So if you like the diagonal, you are in good company with Albert Einstein and many others. And this is why, with a former student of mine, we published this paper and we put as a title, Thermodynamics is more powerful than the role to it reserved by Boltzmann-Gibbs statistical mechanics. Boltzmann-Gibbs statistical mechanics is sufficient for satisfying thermodynamics, but this title says that it is not necessary. You can have other statistical mechanics that also are okay with thermodynamics, and the one I'm talking about is precisely that situation. And a few years later, with Hans Haubold from Vienna, we published this paper to make this point absolutely transparent. And we put as title, Boltzmann-Gibbs entropy is sufficient, but not necessary for the likelihood factorization, etc., required by Einstein. And that paper was chosen by the European Physical Society as a highlight for 2015. So this changes the whole paradigm that relates statistical mechanics to thermodynamics. An important thing in statistical mechanics is the central limit theorem. And the central limit theorem says that in quite general situations, you have Gaussians. So there are plenty of Gaussians in nature because of the central limit theorem. So if a lady comes in with Chanel 5, you smell Chanel 5. And this is a phenomenon of convection, but also of diffusion. And diffusions are Gaussians. If the distribution of the color of the skin, of the concentration of melanin, are approximately Gaussians. The distribution of the heights of humans or the weights of dogs are Gaussian. And if you take a little coffee and you put sugar inside, and then you do a couple of times like this, a miracle occurs that maybe you have already noticed. The entire coffee becomes sweet. It's fantastic. You put sugar just on one part, you do a couple of times like this, and all the coffee is sweet. Incredible. There is a number of phenomena involved, but one of them is diffusion, Brownian motion, which is Gaussian. So the world is full of Gaussians. In this room, we would easily find dozens of them. But in this theory, in the Q statistical theory, instead of Gaussians, we have something more general, Q Gaussians. So during many, many years, I was looking for generalizing the central limit theorem in order that it would be natural to find Q Gaussians everywhere. And that was accomplished with two mathematicians and Marie Gell-Mann, the mythical Murray Gell-Mann, who invented the word quark for the quarks. And this turned out to be also an important ingredient within this theory. Applications of this, proofs, experimental proofs or numerical proofs that these ideas have some sense, it's very hard to make a selection, but I selected a few of them. And I would like to start with that one, a slow chemical reaction. And that paper was published a few months ago in Nature by a group from Innsbruck in Austria. And they made experiments for a simple chemical reaction, which is that one, deuterium plus hydrogen equal this. And because the masses are not very large, quantum mechanics turns out to be important. And as we all know, a chemical reaction is a minimum here and another minimum there, which is deeper. And the system is here and would like to go there. But to go there, it has to go through the hill. But because this system is quantum, it doesn't have to really go to the top of the hill. Before going to the top of the hill, it makes tunnel effect, quantum tunneling, and goes to the other side. So there is a non-local quantum effect there that makes that chemical reaction different from the other chemical reactions. And this paper was chosen as a highlight in Nature, and that was their highlight, rate of quantum tunneling reaction revealed. And this is the paper by these people from Innsbruck. So when I saw the paper, in this paper, they have this figure, and in this figure, they show that for two different concentrations of hydrogen, they have two different values of Q, which are not one. So the distribution of velocities is not the famous Maxwellian, is not Boltzmann-Gibbs. It is a Q Gaussian. Here you have a Maxwellian. So I contacted the leader of this group, Roland Wester, and I told him, I saw that in your paper, you have some pages related and discussing Q Gaussians, but you didn't give the values of Q of your figure. And then after a few days, he answered, oh yes, we didn't indicate the value of Q. The values of Q is 1.23 and 1.15, etc. So with this and these values, I suggested a conjecture. Q minus 1 equal, this is the 2 points that Roland Wester sent me, and it is proportional basically to the concentration of hydrogen power 1/4. So you see here and here the two experimental points. Here, the ideal gas, when the density goes to 0, Q goes to 1, and the ideal gas must be Boltzmann. And so I am conjecturing this. So as Hans mentioned and Adrian mentioned, why this has good chance of being correct? Because it's very beautiful. It's very simple. Q minus 1 proportional to us 1/4 exponent of n. So I suggested to the guys from Austria to make more experiments to see whether this is correct. he told me those experiments are very hard to do. And okay, so I'm waiting somebody to do these experiments. Long-range interactions. And I told you that we arrived to that conclusion with Roger Menard analyzing the paper by the Plastinos. But for long-range interactions, it is very interesting to see what Gibbs said in 1902. So in his book, Elementary Principles in Statistical Mechanics, he invented the expression statistical mechanics after thinking more than 20 years, because mechanics is deterministic. It is Newtonian mechanics at that time. And statistical is a sort of contrary to the determinism of mechanics. And this expression is appropriate if you think that the air is made of molecules that do like this. But Aristotle said that fluids belong to the mineral kingdom. And the basic characteristic of mineral kingdom is not to do this. So Gibbs didn't want to use the expression statistical mechanics because it was opposite to where most physicists were thinking at the time, because the physicists at the time were thinking what Aristotle thought. In Middle Ages, they used to say, Aristoteles dixit. That was a final argument. If you had a discussion, and in a certain point you quoted Aristotle, and you said Aristoteles dixit this, that was the end of the discussion. So that was the power of Aristotle. So it took him 20 years to decide to publish this expression. And in this book, in page 35, he says that if some mathematical thing, the partition function, is infinite, if it diverges, the law of distribution becomes illusory. What law of distribution? His law of distribution. Gibbs is writing that his law of distribution, to which is dedicated his entire book, is an illusion if some quantity is not finite. And more than that, Gibbs, and I was very near his tomb in New Haven 1 month ago, and Gibbs gave an example of this. He says, and it excludes material points which attract one another inversely as the squares of their distances, gravitation. So Gibbs knew that his theory, statistical mechanics, is not correct for gravitation. And I have reasons to suspect that Boltzmann also knew that. And thousands and thousands of physicists, chemists in the world don't know that. They think Boltzmann-Gibbs statistical mechanics is universal. And it is not. And Gibbs knew that. And he wrote it. So maybe this is not important. Let me go to this paper in which we worked together, Antonio Rodriguez, who is here, Fernando Nobre, who is, he is there, and Cirto, he was a former student of mine, and myself, and we put as a title, Validity and Failure of the Boltzmann weight. Because some people tell me, oh, so you are saying that Boltzmann entropy is wrong? No, I never said. I think that Boltzmann entropy is correct. fantastically correct for these classes of systems. And it does not apply to those classes. So we are suggesting another expression that applies in both, here and there. So in this work, we have this figure, which is in log linear scale, the distribution of velocities as a function of the velocities. And this is a Maxwellian. This is a Gaussian. And these dots is not a Gaussian. And we check that for 1, 2, 3 dimensions. So here, where we were using here, where we were using exclusively force equal times acceleration, so from first principle, we obtained a Q Gaussian. So the books say that always it's a Gaussian. They should say that it is always if the interactions are short-ranged. If the interactions are long-range, it is not a Gaussian. This Gaussian is a pillar of Boltzmann-Gibbs statistical mechanics, and it is not true here. And then I went directly to the heart of Boltzmann-Gibbs statistical mechanics, which is the Boltzmann-Gibbs weight, the formula that Gibbs said is illusory. It is wrong. Gibbs said that his law is wrong when you have long-range interactions. And he was right. It is wrong. Here is Q equal 1, which is what is taught in the books of statistical mechanics in the world, but the system does not like it. What it likes is this, and this is a Q exponential. I will skip this, it's not so important. I will skip also this. Now let us go to a different system, granular matter, which means a lot of grains, like stones or small stones, or the flour with which good cookers can make a nice sweet granular matter. So in '95, I was in Michigan, and I received a paper in an envelope by the two Plastinos, another paper. And that paper, 95, it had a connection between anomalous diffusion and the entropy, basically. So they showed that if you take a particular form of anomalous diffusion, it is connected to Q entropy. And I was very surprised because of that, and I started working on their paper. And I advanced a little bit more along the same path they were, and we found a scaling law, a little formula that I waited for nearly 20 years that somebody checks if it is true. And it was checked after this time by this group in Grenoble, the town of Roger Menard. And they verified that the little formula that you see here is correct within 2% of error. So after exactly 19 years, they validated the prediction that Bookman and myself had done, inspired and following along the lines of Plastino and Plastino 95. This paper was considered so remarkable. I was invited at the offices of American Physical Society in New York State to give a colloquium to all the editors of the American Physical Society, the editors of Physical Review Letters, Physical Review A, B, C, D, E, the Review of Modern Physics, etc. And finally, their paper was published in Physical Review Letters as an editor's suggestion, experimental validation of a non-extensive scaling law. High energy collisions. These connections started long ago with a remark by Ignacio Bediaga, who is here, and they published a paper, the two of them, with Evaldo. I made a colloquium in CBPF, and one day after, Ignacio arrived to my office, tell me, look what happens when you have electrons and positrons that collide together. And finally, a paper came out, and it was the beginning of Q statistics in high energy physics. And here you have the LHC, the famous Large Hadron Collider, 27 kilometers of accelerator below the Earth, below the ground. And you have 4 detectors here, and here you see the ALICE detector. Here you have a human being, so you can see the size of these detectors. And they did a workshop there on Q statistics for high energy physics, and they invited me, and they took me down there, and it's like a film of James Bond, because you enter in the elevator, and the elevator checks the eyes of the guy. They don't want somebody to put a bomb there. And at almost 100 meters below the ground, they invited me to take a coffee and everything, and I was very, very impressed seeing all this. And I thought, well, I don't see James Bond, but I would like to see the girls of James Bond around. They didn't show, but they took me around down there, and they told me at a certain point, this door closes the detector when it starts working. And they told me, say the weight of this door. So I looked at the door like that, or iron, whatever. And I said, I don't know, many tons. More than the Eiffel Tower. What? Yes, the weight of this door is more than the Eiffel Tower. And it takes 2 days to close it. Oh my God, I said, can you take me a picture with this door? And here you have the picture. So there they found evidence, impressive evidence of the applicability of Q exponentials here. In this picture, I will not enter into details, but in this picture, there are at least 2 remarkable facts. The first is the talent of the experimentalists that in a single experiment, they can cover 14 decades, 14 experimental decades. So to do this, they must work with a precision which is 0.001 0, 0, 0, 0, 0, 14 zeros, and then a digit. So it's amazing. And the second amazing thing is that all these are well fitted by a simple Q exponential that you see here. Here, these and these and these and these are Q equal 1.14. And here you have Boltzmann, Q equal 1. So in this region, Boltzmann is not 20% wrong or 30% wrong. Here, Boltzmann is billions of times wrong. Is terrifically wrong. And Q statistics is okay. This value, dozens of people had asked me since these things came out, do you know why Q is 1.14? And I always had to answer, I don't know. It is 1.14 for different energies and different detectors, but I don't know why. And the answer came from first principles, as it should. Maybe I will skip this. By a paper by Ayrton Deppmann, who I think, yeah, he is there, Eugenio Mejías from Granada, and Deborah Menezes, who was the former president, the first woman to be president of the Brazilian Society of Physics, and today has an important position in the Ministry of Science and Technology. So these three people found a marvelous little formula, which is that one, where this is the number of colors, and this is the number of flavors of the quarks. And when you put 6 and so the other way around, 3 and 6, this little formula gives you Q equal 1.14. So from first principles, today, we know why at CERN we are measuring 1.14, which we didn't know since maybe 20 years, but today we know, thanks to this paper. And let me skip this. Let me tell you that random networks that are so important in economics, in neurology, and many other things also follow Q statistics. Something like this, which you could think is, for example, connections of computers or connections between neurons in the brain or the circulatory system of mammals. Well, for this, the answer is Q exponentials with this expression of Q. Let me show to you another example, the logistic map. So the logistic map has a parameter, A, that you can choose wherever you want up to 2. If you take A equal 2, you have strong chaos in the system. And when you have strong chaos, if you put here Boltzmann-Gibbs entropy as a function of time, you get a straight line, longer and longer and longer, depending on whether the partition of the phase space is thinner and thinner and thinner. So you have a straight line. And why it is important to have a straight line? Because this straight line is the entropy production per unit time. And you would like it to be a finite number, not 0, not infinity, a finite number. And this miracle of having a straight line is done by SQ. equal that of Boltzmann. So Boltzmann works here. But the logistic map, you can take A equal a special value, which is called Feigenbaum point. And here, there, you have fractals, multifractals, you have a lot of things. And there, you can also have a straight line. Here you have it. And it is longer and longer and longer when your partition is thinner and thinner and thinner. But to have a straight line, you cannot take Q equal 1. You must take a special value of Q, which is 0.24. And then you have a finite entropy production per unit time, only for this value. This was first found by Plastino Jr. and a Chinese that was visiting CBPF and myself in '97. And then it was seen with more details by Marcelo Lira from Maceió, and then it was seen again and again and again by Alberto Robledo from Mexico. And today, this value of Q is here with 10,000 digits. So it's not analytical, but it's 10,000 exact digits. So it's almost analytical. And I should stress that this number is not of a Q exponential. This number is of a Q entropy. So it's really the origin of Q exponentials. Angel Plastino said in his talk that some authors prefer Rényi entropy or this or that. Great. So when you only check the Q exponential, you are not completely sure that it comes from a Q entropy. But what I'm showing to you here is 10,000 digits of a Q entropy. I'm showing to you the foundation of statistical mechanics. Gravitational systems. So there we have our friend Hawking, who published a famous paper, 76, and he called it black holes far away in the stars, black holes and thermodynamics. And this is the abstract of Stephen Hawking. And this abstract, it's fantastic. It is the proof that if you are a very important person, you can publish whatever you want. Because in this abstract, he says, we have a large number of configurations. The logarithm of this number can be regarded as the entropy. What is the entropy, which is the logarithm of W? Boltzmann. So in this part, here, he's using Boltzmann. But here, he says that the distribution of energies cannot be applied when you have gravitation. This is what Gibbs said in 1902. But this is a consequence of this. So in the abstract, he has a deep contradiction, because he uses Boltzmann here, but here he says that the necessary consequence of Boltzmann is not applicable. I think that if this paper was sent from Latin America, it would have never been accepted. But it was sent from Cambridge by Stephen Hawking, so it was accepted. And this is the origin of the famous Bekenstein-Hawking entropy. So I said, I thought, it's not possible because here he's right. The Boltzmann-Gibbs statistical mechanics is not applicable. And then I suggested a different entropy for black holes. This paper started in a meeting, in a symposium that was done inside the Vatican, in the Academy of Sciences of the Vatican, who have something more than 30 Nobel Prizes among their members. They made a meeting about high energy physics, etc. And they invited me to be there. And we were every night sleeping in the hotel where slept, or maybe I think he's still sleeping, the Pope, Santa Marta. And I was in one of the rooms that the cardinals use when they vote for the Pope. And of course, the park is absolutely wonderful, and the room, the marble is wonderful, and everything is wonderful, but it is terribly boring. So I didn't know what to do in the evenings. And there was some discussion in one of the sessions in which the case came out, what is the entropy of a black hole? So I started, not having nothing to do, to work out if I could find the value of Q for which the black hole's thermodynamics would be okay. And I didn't find it. One night, and another night. And then suddenly I thought, I know, I will never find it because there is no value of Q for which SQ is the correct entropy for black holes. Black holes is not Q statistics. So it must be a different entropy, not Boltzmann, not SQ, some other entropy. So I invented one that I had as a mathematical exercise in a book. And here you have the expression of an entropy which depends on two indices, Q and delta. If you take delta equal 1, you go to the SQ I'm talking now. But if you take Q equal 1, you go to the S delta. And if both Q and delta are 1, you recover Boltzmann. So at that night in the Vatican, I said, it's useless to work out on this. I will never find a value of Q that works because it's not SQ. It is S delta. And I found a delta for the black holes, which is 3/2. Delta equal 1.5. And delta equal 1 is Bekenstein-Hawking. But I found that delta is 1.5. So I was invited in the Department of Applied Mathematics of Theoretical Physics at Cambridge to present these results. And when I arrived there, my host told me, well, here you have the Department of Mathematics. And I looked at it in Cambridge and I saw an entire university campus. I said, all these, many buildings, all these is the Department of Mathematics? And he said, yes. They say that it is the biggest in the world. My God, so many buildings. So I gave my seminar in one of those buildings, and the group of Stephen Hawking was in another building. I was not expecting Hawking to come to hear my seminar because it was so difficult for him to go anywhere. But I had some hope that maybe somebody of his group would come, but nobody came. And so when I finished the seminar, the host said, unbelievable, unbelievable. So looking at him, he says, it is unbelievable what I presented. So I was very happy. But you see the title, Black Holes and Thermodynamics. So on purpose, I put on my paper almost the same thing, black hole thermodynamical entropy. And we say here that delta equal 1, which is Bekenstein-Hawking, is wrong. And maybe delta equal 1.5 is correct. Maybe, I don't know. Dark matter neutrinos. So in the South Pole, there is an observatory, which is that one, which is called the Ice Cube Neutrino Observatory. There in the middle of the Antarctic, South Pole. And they measure neutrinos there. And this paper appeared 1 year ago, I think 1 year ago. And they have the crossing of this curve, and this point gives the perhaps correct interpretation of the data they are receiving from the universe. And this point is 1.565. So I said, my God, very close to 1.5. So this suggests that our prediction, 3/2, might be correct, and definitively it suggests that Bekenstein-Hawking is wrong, because 1.5 is far away from delta equal 1. 1 year after, the data arrived from the Planck Observatory, the European NASA. And this is there, not in the South Pole, in another place of the world, turning around. And they have data concerning neutrinos. You have a big expert in neutrinos, I think, in the room. Wagner is here. Yeah, there. He's one of the most famous experts in, theoretical experts in neutrinos. Wagner, José Wagner Furtado Valle, with whom we had a paper at the time he was a student in PUCI. And one day he told me, why don't you give me some exercise to do something so I understand a little bit of statistical mechanics? So I gave him an exercise and we made a paper together. And these people from Iran published this year the data upstairs there in the space. And they have two tables, that one and that one. And that one suggests delta equal 1.87, which is above 3/2. And the other approach suggests delta equal 1.26, which is below 3/2. And I said, well, they don't know exactly. So I said, what about if I do the average? What about if these two are something like an upper bound and a lower bound? So let me make the average. So I made the average of this number and this number, And I had one of the big surprises of my life. It gave 1.565. The average of the Iranians is exactly the same as this in Czech and Italy. So I wrote to all of them, I don't know if you are aware, the average of your numbers here is exactly the number that you have in your paper there. And if you have any comments, please tell me, because I am stupefied by this incredible coincidence. And they answered to me several comments. Okay, and then to finish this, a few weeks ago appeared, or maybe, 10 days ago, appeared another paper from the guy from Czech Republic and Italy, a different approach, invoking category principle, etc., and they found delta equal 1.499. So maybe delta equal 1.5 is the exact answer. And to finish applications of Q statistics that we have heard so many this week, this came from Islam, from Iraq and Malaysia, and they discussed the computer tomography of COVID-19 with Q transform. And this is what they found. This is a section like this on the lungs. So here you have a fibrosis due to COVID-19, and they processed the same data with Q equals 0.5, and they found this. The same patient. If you are a doctor, you prefer surely to make your diagnostic here and not here. This is a second patient. Here you have the fibrosis, and here you have what happens if you use Q different from 1. And a third patient, and here, this is the normal one, and this is the Q equals 0.5. And Dr. Watson asked one day to Sherlock Holmes, how do you find who is the murderer? And Sherlock Holmes answered the relevant details. So, if the relevant detail was this little dot here, you see it here, and you don't see it there. Well, these two books were shown by Hans. So let me go to a take-home message. Simple systems refer to local space-time correlation, for example, exponential decays. And when you have this, you must use Boltzmann, Gibbs, von Neumann, Shannon, additive entropy. And this leads to Boltzmann-Gibbs statistical mechanics, which is taught in all the courses of physics and chemistry and computational sciences around the world. But in the complex systems, you have non-local space-time correlations, for example, power laws, and these lead to non-additive entropic functions like SQ or S delta, and then you must use generalized statistical mechanics. And since the word correlation has an important place in this message, I want to make the distinction of interaction and correlation. So if you put a domino on the table, the length of interaction of a domino is its height, here and here. This is the length of interaction. So if you put randomly on the table, here, you must apply Boltzmann-Gibbs statistical mechanics. But if you put them like this, the same domino, the length of interaction is still the same. It's a short range interaction. But if you put them like this, you hit one of them and it goes forever. So the interaction length is short range, but the correlation is long range. And that brings me to José Ortega y Gasset, who wrote, Yo soy yo y mi circunstancia. I am myself and my circumstance. I'm not only myself, I'm also my circumstance, the context in which I am. So here it is Boltzmann, and here it is not Boltzmann. We had beautiful discussions with Giorgio Benedek in Italy, and a colleague of us in Spain, and some people in Turkey. No, was it? No. There was somebody else. About what was the correct translation of Ortega y Gasset's statement, and whether it was in mis circunstancia or in mis circunstancias. But the correct is in mis circunstancias. We decided and we checked that Ortega y Gasset was very rigorous, because circunstancia is only one. It is circum, what is around you in all senses, around you. So it is one circumstance. It's enough. You don't have to use the plural. So it also gave to us the occasion of make a lot of discussions about linguistics. And approaching the end of what I wanted to tell you, here you have Sanders, Charles Sanders Peirce, that was mentioned by Guiomar in her talk. And you have here logical inferences. So deduction is all the stones in box A are black. This stone is from box A. Therefore, it is black. This is deduction. And it has the strength of a proof. Induction. This stone is from box A and it is black. This different stone is also from the same box and it is black. And the third stone is from the same box and it is black. Therefore, all the stones of box A are black. And this is not, it has not the strength of a proof, and it cannot be used in mathematics. But then Giuseppe Peano, this man, completed this with the Peano's axiom, and he transformed induction into complete induction. And that one has the strength of a proof. So these two were very much discussed by Aristotle. But this man introduced that one. So here, all stones in that box are black. That box is black, and therefore it came from that box. And this might be wrong, because maybe it is black, but it didn't come from that box. It came from somewhere else. But doing this abduction, it opens the scenario for you to check, like Sherlock Holmes, to check if it is true or not. And the scenarios are important. As Seneca said, the Roman philosopher, there is no favorable wind for the sailor who does not know to what port he is going. So you must know where you want to go. So this is what abduction gives you. And 1 month ago, I was giving, they invited me to give a seminar in Princeton. And I went a quick visit to Maldacena at the Institute for Advanced Study, which is very beautiful, as you can see. And the symbol of the institute that was made famous because of Einstein is this, which is truth and beauty together, giving hands. The truth is naked. Beauty is almost naked, but not naked. So this made me remember that the Academy of Athens, which you see here, has in its front Socrates and Plato, and the Academy of Athens is not Academy of Sciences. It's Academy of Athens. It's sciences and arts. And in Greece, it is not called Academy of Athens. It is called the Academy, the one that came from Plato. And what do you have in front of the Academy? You have the goddess Pallas Athenea, who is the goddess of science. A woman is the goddess of science. And on the other side, you have Apollo, who is the god of arts, a man. So in most countries in the Western world, it's the other way around. But in the Academy, the science is a woman and the art is a man. And since we are talking about Socrates, Plato, who was a student of Socrates, he had a famous student, Aristotle, who gave what is close to what I think to be theoretical physics as compared to experimental physics. So Aristotle wrote in the Poetica, poetry is more elevated and more philosophical than history. For poetry expresses the universal and history only the particular. History tells us the events as they happened, whereas poetry tells them as they could or should have happened. So theoretical physics is like poetry, and experimental physics is like history. But if they don't go together, it has no value. And that was well established by Galileo. And since I'm talking about Aristotle, here you have the school of Aristotle, nearby Thessaloniki. And here is the place that was the office of Aristotle. This is where he was teaching to his students, among his students, Alexander the Great, what is a metaphor, what is deduction, what is induction, what are the kingdoms of nature. All that was being taught here. And I would like to, I could not resist to put this by Eddie Cohen when he received the Boltzmann Medal in India. He wrote a paper and he asks, will entropy and statistics continue to play their present dominant role, or will dynamics become more essential for the description of the properties of macroscopic systems? Q, the value of Q, is determined by dynamics. And he mentions Boltzmann concludes his lecture by indeed interesting questions. One almost regrets to have to die long before they are settled. I always think that, my God, I will never know the general expression of Q. I will die before. O immodest mortal, your fate is the joy of watching the ever-shifting battle, but you will never see the outcome. These wings and that, wings and that, and you will never see the outcome of the battle. Men of science have made abundant mistakes of every kind. Their knowledge has improved only because of their gradual abandonment of ancient errors, poor approximations, and premature conclusions. He is an American historian of science, and I would say that nunca es tarde si la dicha es buena. It's never late if you have something good in hands. Just do it. And I think this is my last slide. I would like to tell you that I dedicate this talk to Maria Cristina Frascarol, to Maria Aparecida de Oliveira Prado, to Marisa Lopez, to Alexandra, to Adrian and Emmanuel. And then I will not dedicate this to my grandchildren, because their parents one day will dedicate in turn to them a talk like that one. So I would like to finish with this. Let me paraphrase Tolstoy in his fascinating Anna Karenina. Detractors are all alike. Collaborators and real friends are so in unique manners, which are all theirs. La gratitude est la mémoire du cœur. Gratitude is the memory of the heart. Thank you very much.